But Steve requested you. Okay, so what am I supposed to do?
And if we can anyway formulation, we get to the. We're supposed to do the actual visual and the anyway. And the more of the list of components I have here in my income for it. What is a little up the neck? I achieve something that is a competitive thing. So I can just, because they first, why we find there? Is still be one that you know would need to. I think, so it was, I think it's still, I heard something that required.
Yeah, I mean, the policy is always going to say it won't be hard information, but then you.
Yeah. Yeah, it's used to be. Yeah, that's nice. It's not very fantastic. It's got to be that's. What I would so obviously not shot. I mean, at some point, so music publishing ball here home, so music publishing. Usually. No, I think that the thing is changing yeah, one of the very big. So why did that one contribution? I think the focus is the primary one. Yes, you're able to reach so like there's no contribution higher with the science. The scammer is more. This these are cool. They're good. I guess with my I don't understand so. It's like you did programs really go. I think what is the base of the I think it's an edge. I injected a like a strong red note in there as a from the visual of the yeah. What makes it insane is why when without it, so it's going after. This is more correct than this, which shows how I hate correct formulation. You don't look at yeah, okay. You go to the one parameter,
Unusual. What did I put? Tile?
Yeah.
Oh, I'll fix that. I'm sorry. Yes, yeah.
Yeah, yeah. If you follow this, in something fine, you know, also, you should say, I guess, working. So you say you will have a good year. So that like at 0.35, the old one that is, you should have, spot skills and local levels. I'm talking about, like, the other structure of mind, like, if you go to a more complicated, also, does go work. If you turn it down, points down to certain down points that would require. So, here's that. That's not my shoulder. Yeah. You can keep it, and you hold the number, you could, and still possible, go back.
Well, I didn't check, so if you want.
Have as many components as you live, or you could have 200 or 100. What is it for? I just want to have.
Cool. And you shouldn't need to connect via audio because everything is going to feed through. Yeah. So I'll probably do introductions in about 5 minutes and
Yeah. So this day, if this is too much.
so welcome in everyone. We'll get going in about 5 minutes. If you haven't had a chance to get some snacks or coffee, it's at the back of the room. Check the Slack for a map of how to get to restrooms and the elevator to go downstairs if you need to. Otherwise, EduRoam is your best bet for Wi-Fi, or there's VU Guest as well. And if you need power sockets, they're in the roundy metal things at the bottom of the floor there. Just flip them up and there should be some outlets. Okay.
You want to. Sorry. Yeah. Beautiful story. Yeah, very good. So Yeah. How do you say customers what there's movie? Whatever they need there. Okay, oh, and I want, you're going to be that, that's the city that I this. And go to. That's cool. You're going to stay wrong. Yeah.
Okay, everyone, let's make a start. Welcome to what is the third iteration of this Pulsar Timing Array Summer School. It's really a pleasure to have you all here. I know some of you traveled quite far. And those who didn't travel far, I know it's a slog to come across the country, especially near thunderstorms and travel disruptions. It's been interesting to host this summer school from 2022 until now, because the field has obviously changed quite a bit. We've gone from the hope of seeing something to having something and now trying to characterize it better. So I'm hoping that the next 2 weeks will give you an opportunity to get to grips with some of the basics of gravitational waves, pulsar timing, things that you probably know well before, or if you don't know them, this is a chance to refresh in some of those basics. And then some hands-on activities, learning some of the more modern tools, including newly developed pipelines for data analysis and even timing itself. And interspersed with kind of the lectures is hack time. And this is something that we'll ramp up on in the next few days and really get going on in the second week. And that'll be an opportunity for you to take what you're learning in the summer school and actually translate it into mini projects. And you'll have seen that I kind of seeded some mini projects ideas. Those don't need to be the ideas that you work on. They really are just to get your mind working on possible topics. But I'm hoping that at some point over the next few days, you start to find that you have common interests with some people. Maybe the mini projects that I've seeded are the best way to do that. And then just start talking with each other and working on things. And I'm hoping that you also get something out of some kind of result, a plot, or just the start of an idea by the end of the 2 weeks. The most important thing is that you get to know each other, because you are the new either graduate students or postdocs working in this field. And so really getting to know each other is the most important thing, because you'll be working together in the field for hopefully won't be many years to come. All right, so we're really starting off in the basics of gravitational waves this morning. We're starting off with Kristen Schumacher, who's very nicely decided to come along and give us a primer on gravitational waves. And you'll see that we get more and more specific on pulsar timing arrays as the next few days goes on. We'll have lectures this morning, and then since we're going to be doing some actual hacking, we'll try to set up some kind of software help desk this afternoon, make sure that you have no problems getting things installed. And then we'll do more proper introductions at the end of today. Okay, so Kristen, if you'd like to come up. And let's make sure that you get connected, okay? So we're on Zoom, and we're also streaming live on YouTube. So that's, I guess, just something to be aware of.
Stop sharing.
I hid the meeting controls, so now I have to get them.
Escape.
Nice.
It's working.
Thank you.
Just make sure that we can see. Yes, cool. All right. Great. Thank you, Steve. Hi, everybody. As you said, my name is Kristen. I'm a postdoc. Today I'll be talking a little bit about gravitational wave theory, as he said. So since we're all here for a PTA workshop, I figure it's safe to assume that everybody here is probably somewhat interested in gravitational waves. And you probably don't need me to tell you why these are such an interesting signal to search for. So what I will try to show you over the course of the next hour and a half instead is how we can predict the existence of these gravitational waves directly from the Einstein field equations. Obviously, to be able to measure these waves, we need to know how to model them. So we're going to touch briefly on the kinds of sources that can generate measurable gravitational waves. And I'll also talk a little bit about how the amplitude of the waves scales with different source properties. So first, can you please raise your hand if you've taken GR? Like, yes, I have taken a GR course. Great. Can you keep that hand up if your GR course got through gravitational waves? Cool. Okay. So for most of this is review, but please ask questions as you have them. Yeah, so let's start with conventions and a little roadmap of where we're going. So first, I'm going to use the quote unquote correct metric signature in GR minus plus plus plus. In particle physics, they use something different, but this is what we're going to use here. I'm going to work in geometric units. So we're assuming G and C are equal to 1. I'm not going to write them everywhere. You can put them back in with dimensional analysis later. For indices, I'm going to use Greek indices to represent space-time. So these range from 0 to 3. Latin indices, yeah, you want bigger? Yeah.
And then is everyone back here?
Let me flip it this way and then we can make it a little wider and still be seen. Is it still big on the screen? Okay, yeah. Good. Right, Latin indices for space. So those go from 1 to 3. I'm going to assume we're using the Einstein summation convention. So anywhere we have repeated indices, we're summing over them. We can also replace repeated indices with a different index. That's totally fine because it's being summed over. So we can change the name of that index for free. Partial derivatives are written like this. So like partial mu, and that's like partial with respect to x to that index mu, okay? Remember that partial derivatives commute, so we can swap those around for free. And we're mostly going to be working with partial derivatives today instead of covariant derivatives, okay? Great. I will also post these notes after. They'll be on GitHub. So don't feel like you have to frantically scribble every bit of math down. It will be available. I just want to go through derivations carefully because it doesn't make sense to me unless I write it out personally. All right. So our first goal is to linearize the Einstein field equations. So we don't have time to derive the field equations today. I'm just going to give them to you. So we have G mu nu equals 8 pi T mu nu, again, neglecting factors of G and C, because we're working in geometric units. I'm going to call this equation 1. On the left here, this G mu nu is the Einstein tensor. This describes the geometry of the spacetime. And on the right, this T mu nu is the stress energy tensor. Okay, and that describes all of the energy and matter in our spacetime. Okay, so of course, wrapped up in this simple line are many coupled nonlinear partial differential equations that are actually very tricky to solve. But we can boil this down to the quote, "Spacetime tells matter how to move." Right, which is like the left-hand side of this equation determines where the right-hand side goes. And then the second half of this quote, matter tells space-time how to curve. That was John Wheeler's quote, and everybody uses it. So that second half, right, is like the matter here on this side is affecting the curvature on the other side, right? Okay, so that's the Einstein field equations, a little bit of a roadmap for where we're going. So we're gonna start with the space-time metric, G mu nu. From there, we can construct the connection, which is gonna be labeled gamma, right? And the connection is a function of the space-time metric G and derivatives of that metric, so partial G. With the connection, we can construct the Riemann curvature tensor, right? So this is a 4-index tensor, and it's a function of the connection and derivatives of the connection. From the Riemann curvature tensor, we can build the Ricci tensor, which is just like, we can get that from contracting over the first and third indices of the Riemann curvature tensor. Taking the trace of the Ricci tensor gives us the Ricci scalar. Right? And then we're going to be able to use these two quantities, the Ricci tensor and the Ricci scalar, to construct the Einstein tensor. Because that Einstein tensor, G mu nu, is equal to R mu nu minus 1/2 G mu nu, where that's the space-time metric, times R, the Ricci scalar. Okay. Once we have that, we can plug it back into equation 1. And when we have this fully linearized Einstein field equations, we're going to look at that and go, hey, is that a wave equation in there? And from there, we'll keep working with gravitational waves. Okay, so that's just a roadmap of where we're going before we dive into the nitty-gritty details. So let's start with the space-time metric. So first, we can make an assumption that we can split our space-time into a piece that's flat and a piece that's not flat, right? So I'm going to write this as G mu nu is equal to eta mu nu, where this is the Minkowski metric, plus some small h mu nu, and this is like the rest of the curvature in our space-time. It's some small perturbation. All right, eta mu nu, that Minkowski metric, can be written out like -1, +1, +1, +1, and everything else is zeros. And for everything that follows here, we can assume that h mu nu is really small. So we'll say much less than 1. Because of that, we can neglect anything of order h squared. And that's going to dramatically simplify these equations as we go. All right, so if this is our metric, our inverse metric will look like this. G mu nu equals eta mu nu minus h mu nu. And it's pretty simple to check that this is the right inverse metric. So let's do that just as a little review of how to manipulate tensors in case it's been a minute. So we'll take our inverse metric multiply by our regular metric. So here, eta mu nu minus h mu nu times eta mu nu plus h mu nu. All right. Expanding that out. And then we have something that's like order h squared. So these two cancel. We neglect order h squared. We're left with just this contraction over the eta mu nus, which is just the Kronecker delta, which is what we expected from taking the metric times its inverse, right? So that's great. That's the right inverse metric. Okay. So since we are going to neglect order h squared, excuse me, since we neglect order h squared, for all the other tensors, we're going to be able to raise and lower indices with the Minkowski metric instead of using the full spacetime metric, right? So that's also going to simplify things. So that means the inverse of H alpha beta, we can just use the Minkowski metric. Okay. All right. Now that we have the metric, we can build the connection. So in GR, oh, and I want to say that because my PhD was mostly focused on modified theories of gravity and things that go beyond GR, I'm going to try to flag places where GR specific assumptions come in. Because first of all, these are really cool properties of GR. And second of all, they're things that you can't necessarily assume in every theory. So in GR, the connection is metric compatible. So this means that we can move. So covariant derivatives of the spacetime metric are 0. We can move the spacetime metric in and out of covariant derivatives for free, right? And it's also torsion free. And this just means that it's symmetric on the two lower indices. So these are equivalent, or we could also write this with this anti-symmetrization symbol on those two lower indices. And if you put these two facts together, you can derive the form of the connection in GR. It has to have this form, right? Where it's 1/2 G sigma lambda. So this index matches this upper index, and then the lambda is summed over in all of these expressions. And then on the bottom here, the mu nu here matches these mu nus. Oops. Right? Okay. Now, if we plug in the spacetime metric that we were using above, we're also going to use the fact that any partial derivatives of eta are 0, right? Because that's just a constant. And we're going to neglect order h squared like we've been doing. So when we do all of that, we can rewrite this connection as 1/2 beta sigma lambda. Because we're neglecting order h squared, there's no h out here. And then partials of the h's. Okay, we'll label that equation 2. Good so far? Does anyone need me to slow down, speed up? We're good. Okay, great. All right, so now we have the connection. We can go to the Riemann curvature tensor. So the Riemann curvature tensor, like I said, 4 indices, it's a function of the connection and derivatives of the connection. I'm going to give you that formula here. You could derive it yourself, but we won't do that for the sake of time right now. But I think it's useful to know that you can derive it using the commutator of covariant derivatives. And Carroll walks through a nice example of this in his textbook, right? Where we can understand the curvature of the space by like taking covariant derivatives in one order and then taking them in the other order. And we get to the same point, but because we went different paths, now we know something about curvature. All right. Also, this formula holds for any connection. So that's good to know too. All right, so we have this formula and we have this equation 2 up here for the connection. So we want to plug equation 2 into this expression. First, we're going to note that the connection up here in equation 2, this is of order h, right? Every single one of these terms is of order h. So that's going to mean that anywhere we have 2 connections together, that's of order h squared. So we can drop those terms. Okay, so if we drop those terms, then we just have the first two. So R rho mu sigma nu is like partial sigma gamma rho nu mu minus partial nu gamma rho mu sigma. And then plugging in equation 2 for each of these connections, we have 1/2 eta rho lambda partial sigma partial mu h nu lambda plus partial nu h lambda mu minus partial lambda h mu nu. And then similarly for the second one. Okay. If we expand all of that out, so like pulling these partial derivatives into the parentheses. Oh, and notice it's the same eta rho lambda on each term and 1/2, so we can pull that out to the front. Okay. And now we're just doing algebra. All right, and then the second parenthesis, so we got minus partial mu, h sigma lambda. Again, one more time. Okay, that's a long expression, but hey, two of these are the same. We can cancel those two terms, so that gets a little bit simpler. Not a lot, but a little. And all together, we have R rho mu sigma nu is equal to 1/2 eta rho lambda partial sigma partial mu h nu lambda minus partial sigma partial lambda h mu nu minus partial mu h sigma lambda plus partial nu partial lambda h mu sigma. Plus, of course, terms of order h squared. We're neglecting those. Good to remember they're still in there. If you ever want to do this calculation again, you'd have to carry it out a little more carefully, keeping those terms if you want higher order h things. Okay. And let's call this equation 3. All right. So now we have the linearized Riemann tensor. I told you before we can use that to construct the Ricci tensor. We're going to do that next. So R mu nu is just like contracting over the first and third index of the Riemann. If we want to write that out more carefully with eta to raise and lower indices, we can. So we'll use eta sigma lambda, eta lambda rho. So we can just plug in exactly the expression we were using before. And this is just like if we had delta sigma rho. So effectively, we can take all of the rows in our previous expression to sigmas. So I'm going to plug in 3 above. And take all of those. Well, there's only one row, so that's pretty easy, right? This is just going to change that eta term. Okay. And then everything else is the same, so I'm going to take advantage of the iPad and literally copy it. All right, so let's move that eta into the brackets and see how it affects the different terms differently. So I can move that one freely through the partial derivatives, right? Because the partial derivative of eta is 0. So I'm going to do that on this first term. I call this partial sigma, partial mu, and then eta sigma lambda, h mu lambda. On the next term, I'm going to leave it outside. Eta sigma lambda, partial sigma, partial lambda, H mu nu. The third term, we'll move it in again. We'll do that again on all. I'll leave it out on the last one. Okay. All right. So looking at this expression, this is just the trace of H. So we'll label that H. And eta sigma lambda times partial sigma partial lambda is actually a very special symbol. We use the box. We call it the D'Alembert when we contract over the indices of the two derivatives, right? This is just the box. Okay, so writing that out again with these two terms replaced, our Ricci tensor is like 1/2 partial sigma partial mu H nu sigma. We're going to use that eta to raise that index on the H, minus box H mu nu minus partial nu partial mu trace of H plus partial nu partial lambda H mu lambda. Okay, so there's an expression for the linearized Ricci tensor, excuse me. Call that equation 4. Okay, now in a Cartesian coordinate system, this box thing, box of H, can be expanded out like this. It's like minus partial squared over partial t squared plus partial with respect to x squared plus partial with respect to y squared plus partial with respect to z squared H. So if we look at that, box H equals something looks like a wave equation, right? That's cool. So box terms are going to be important. Those are the ones we're going to want to pay attention to. All right. From 4, we can take one more step and get the Ricci scalar. So R equals R mu mu, or eta mu nu R mu nu. So we can plug in exactly the expression we had above. Doing that, R equals 1/2 eta mu nu partial sigma partial mu H nu sigma minus box eta mu nu H mu nu minus eta mu nu, sorry, partial mu H plus eta mu partial lambda H mu lambda. Okay. Whew. So looking at that, well, this is another box. Great. And this is the trace again. So those two terms can be combined. I'm going to use that mu nu to raise both of these indices. What did I do? Oh, yeah, that's right. Okay, mu sigma. Great. Minus 2 box H plus partial nu partial lambda H nu lambda. And hey, these also look the same if we just change the summed over index. Here it's sigma, here it's lambda and nu instead of sigma and mu, but those are summed over so we can make them the same. And then that factor of 2 and so this factor of 2 and this factor of 2 will cancel the 1/2. So we can get rid of that. And this is just like partial alpha, partial beta, H alpha beta minus box H. Whew, cool. All right, I'm gonna call that equation 5. Now, remember back in the beginning, we said the Einstein tensor was equal to the Ricci tensor minus 1/2 g mu nu times the Ricci scalar. So plugging in our equations 4 and 5. First off, I'm gonna just write those out explicitly and then we can make more changes. All right, so 1/2 partial sigma, partial mu, h nu sigma minus box h mu nu minus partial mu h plus partial nu partial lambda h mu lambda minus 1/2. And here r is of order h again, right? So we don't actually need to use the full g. If we were to do that, we'd just pick up more in terms of order h squared. So I can swap this g mu nu for just an eta mu nu. So we use eta mu nu here, and then the partial alpha, partial beta, h alpha beta minus box h from above. We can do this because r is order h. Okay, so now let's pull that 1/2 out. I'll pull the eta mu nu in, group terms together, and I'm gonna write g mu nu as 1/2, and then inside brackets, partial mu, partial lambda, h mu lambda, plus partial nu, partial lambda, h mu lambda, minus partial nu, partial mu, h, minus eta mu nu, partial alpha, partial beta, h alpha beta, minus grouping the box terms together because we think the box looks like a wave equation and those terms are important. Is box h mu nu minus eta mu nu h. Okay. Whew, that was a lot of math. Like, what, 4 pages in? So now we have linearized the Einstein tensor. We've got nothing of order h squared in there, but we can make this simpler. We know the box is important. Maybe we can define a new quantity for that term in parentheses. We could try. It turns out that the math is going to work out a lot nicer if we define instead h mu nu minus 1/2 eta mu nu h. I'm going to throw in a factor of 1/2 there and things will cancel more cleanly. So I'm going to define this new quantity, h bar mu nu equals h mu nu minus 1/2 eta mu nu h. And this is called the trace reversed metric perturbation because if we take the trace of this thing, h bar, which is eta mu nu times h bar mu nu, or eta mu nu h mu nu minus 1/2 eta mu nu h. Right, this first term is just the trace of h. The second term, we pick up a delta mu mu. And that, when we sum over those indices, this is just 4. So we have h minus 2h or minus h. Okay, so h bar is equal to minus h. That's why we call it the trace reversed metric perturbation. We reversed the sign on the trace. Okay. From there, it's pretty easy to get an expression for h mu nu in terms of h bar mu nu and h bar. So let's do that. We have h mu nu equals h bar mu nu minus 1/2 eta mu nu h bar. And I'm also going to write out h mu alpha in terms of the trace reversed version, because that's what we're actually going to plug in below. Okay. So let's plug this back into g mu nu and see what we can simplify. All right, so 1/2 bracket partial mu, partial lambda, and then this was h nu lambda, so that's going to go to h bar nu lambda minus a half delta nu lambda h bar. Okay, second term, partial nu, partial lambda, and then h mu lambda. So h bar mu lambda minus a half delta mu lambda h bar. And then this one was just minus partial nu, partial mu h, which is easy. We just flip the sign. So plus partial nu, partial mu h bar. That's a tongue twister. Okay. Next, minus eta mu nu. Right, minus eta mu nu, partial alpha, partial beta, h alpha beta. So partial alpha, partial beta. Oh, wait, sorry. Let's write this out more carefully. Okay. And now the term in the box. Right, so this was box h mu nu minus eta mu nu h. So h mu nu goes to h bar mu nu minus a half eta mu nu h bar. And then now plus eta mu nu h bar. So flip the sign. Okay. Continuing. I'm going to expand out each of these parentheses. So partial mu, partial lambda, h bar nu lambda, minus half partial mu, h bar, plus partial nu, partial lambda, h bar mu lambda, minus a half partial mu, h bar, plus partial mu, h bar. And then the second line. Okay, and we can combine these and get plus a half. Medium h bar. Okay, wow. So looking at this, we have minus a half partial mu h bar, minus a half partial mu h bar, and plus partial mu h bar, right? So those three are all going to cancel. That's nice. And this is another box. So we can write this as partial mu, partial lambda, h bar, nu lambda, next term, plus partial lambda, h bar mu lambda, minus eta mu nu, partial alpha, partial beta, h bar alpha beta. And then we've got plus a half eta mu nu, box h bar. And let's expand out this box on the parentheses. That's minus box h bar mu nu and minus a half eta mu nu box h bar. And then when we do that, these two are going to cancel. Okay. Now we have a trace reverse version of the Einstein tensor. Okay. And if we remember from way back in the beginning, that's equal to 8 pi t mu. I'm going to call this new thing equation 7. So it's getting better. We're getting rid of terms slowly. We now have a really nice box h bar mu nu term, which is by itself. Can we make the other terms go away? Does anyone notice anything in common between all three of the other terms?
First one.
Okay, yeah, if I can also answer if we don't want to volunteer. Look at maybe if I give you a hint, look at the indices on the partial derivatives and then the indices on the h. Do we have a repeat? Yes, we have a repeat on all of those terms, right? So every one of these involves something that looks like partial lambda h bar mu lambda, where we're contracting over the index on the partial derivative and one of the indices on the h. Okay. So let's see if we can do something that's going to make terms like that go away. Let's try a coordinate transformation. So we're going to take x prime mu equal to x mu, so our original coordinate system, plus some small vector xi mu at every point x beta. And we have to assume that xi mu is also small in order to not break our earlier assumptions about the spacetime metric. Okay, so because xi mu is also small, we can work to order xi. We can neglect order xi squared. So to order xi, the spacetime metric g mu nu prime is equal to g mu nu minus partial mu. Sorry, I picked a symbol that's really hard to draw, so have fun with all the squiggles. Xi nu minus partial nu xi mu plus order xi squared, so we don't care about that. Minkowski metric isn't going to change, so then our metric perturbation is going to be h prime mu nu. H mu nu minus partial mu xi nu minus partial nu xi mu plus order xi squared. Okay, so does this change all of the math that we've been doing for the last, what, now 5 pages? If we recall the Riemann tensor from equation 3, it looked like this. So when we make this coordinate transformation, the change in the Riemann is going to look like that. Not asking you to do it all out, just going to show you. So the only bits that change, right, are these extra terms on the h mu nu, right? So we only have to track those through. So when we plug those in, and we expand out these parentheses, you notice that all of these terms are actually going to cancel, right? This one cancels that one. These two are the same. These two are the same. These two are the same. So the change in the Riemann is effectively 0. The Ricci tensor and the Ricci scalar, and thus g mu nu, were all constructed from the Riemann, so they're all not going to change. So we can take this coordinate transformation without changing any of the math we've already done. Good. All right. But remember, we were working with the trace reverse perturbation, so I actually need to know how this coordinate transformation is going to affect that. So h bar mu nu in this new coordinate system, it's going to be like this. Let's just write out the form of the trace reversed metric perturbation. Applying that coordinate change to both of these, it's like h mu nu prime minus 1/2 eta mu nu h prime. And above, we have the expression for h mu nu prime. So just repeating it here. And then we can take the trace of that to get the one for h prime. Yeah, pretty simply. So I'm giving you that here. We can put these together and get h prime mu nu. So this, we've got, let's plug in the h prime mu nu first. H mu nu. And I'm also going to plug in the minus 1/2 eta mu nu h, And then we have all of the C's and partials, all of that mess. Plus order C squared, which we don't care about. And this is just the trace reverse metric perturbation again. Okay, so we have the trace reverse metric perturbation in this new, after this coordinate transformation, or in this new gauge, right? So we want partial lambda h bar prime mu lambda equal to 0 in the new gauge. And this is actually called the Lorentz gauge. Got a special name because it's a special choice. All right, so to get that, we're going to want to set, we'll take a partial lambda derivative of that expression and set it to 0. Okay. Keeping track of all of the partials and x's. And then plus order c squared. And we want this whole thing to be equal to 0. Now, looking at that, this delta mu lambda term, that's going to take this to partial mu, partial alpha, c alpha, which looks like partial mu, partial lambda, c lambda with the indices swapped. So those can be canceled. Those are the same term. All right. And this partial lambda is the box again. Okay. So this is really like partial lambda h bar mu lambda minus box c mu equals 0, or partial lambda h bar mu lambda equals box c mu. And I'm going to call this equation 8. So to get to the Lorentz gauge, we need a vector C alpha that is going to solve equation 8, right? But hidden inside here is actually 4 equations, right? One for each of the indices, or, 0 through 3 in the mu, right? So we have 4 equations, and there are 4 unknown elements in that vector. So we have 4 equations and 4 unknowns. Which means a solution always exists. So that's great. We can always go to this Lorentz gauge. And if we're counting degrees of freedom, this gauge choice is going to take us from 10 degrees of freedom to 6. All right. Returning to equation 7. I just wrote it out again for you here. Now, in this new Lorentz gauge, we've established that everywhere that we have an index that on the partial that matches one of the indices on the h, that's going to go to 0. So this goes to 0, that goes to 0, this goes to 0. And we're left with minus box h mu nu equals 16 pi t mu nu. Ta-da! We have a wave equation sourced by the right-hand side. Oh, I got it. All right, I think really the round of applause should be for you guys for sticking with me through all of that algebra. Do we have any questions? Your hands cramping from writing so fast. Yeah. Having a hard time hearing you. Can you repeat it? Why is this a gauge choice? So in GR, a coordinate transformation and a gauge transformation are basically the same thing. So we can use the coordinate transformation to get us to the Lorentz gauge. Does that make sense? Does that work?
Yeah. Why? Yeah.
Um,
Because like when you write down all the partial differential equations that are solved, that are symmetric. Well, and therefore, basically, you can make a choice whether it's think that will be four. We have four more equations, we'll see there.
yeah. It's like we have extra equations than we need.
The fact that you can make a coordinate on your under the term disappear because they're unphysical, they don't have physical freedom.
Right.
Is more reason why you can just reduce it down to the way that what the supposed to term, right? So,
Yeah, and at this point, there are 6 degrees of freedom still. We're gonna continue. And I won't go through the details, but in GR, you get all the way down to 2 degrees of freedom because we're gonna take another gauge transformation in a minute. In modified theories of gravity, you can't do that. And some modified theories of gravity are left with 6 physical propagating degrees of freedom still. And you can also see that as like the 6 linearly independent components of the Riemann tensor. Okay, shall we continue? So in a vacuum, far from the source, this is just going to be box h bar mu nu equals 0, which is solved by or can be solved by h bar mu nu equals a mu nu e to the I k sigma x sigma, where k sigma equals 0. So this is a null vector. And in GR, gravitational waves are going to travel at the speed of light. Not necessarily true in every theory, but a very cool property of GR. Okay. As we just said, in GR, we can remove another 4 degrees of freedom by moving to the TT, transverse traceless gauge. I'm not going to go through all the details because I think it's easier to see if you write the metric perturbation out in terms of all of its components. And they do this really carefully in the Poisson and Will textbook over the course of like 4 different sections. So I think that's probably a better place to look for it than to do it here. But in the TT gauge, what we're left with, we have this H bar, JK, and the transverse traceless piece is the only piece that radiates. So in this gauge, the 0, 0 component of the metric perturbation is going to be a constant. It's not varying with time. It's not going to radiate. And H0I is going to be 0. So all we are going to care about is this HJK piece. This is transverse. So partial J, H bar JK TT equals 0. And it's also traceless. So if I take delta IJ, H bar IJ, TT, that's going to be 0. All right. Let's choose our coordinate system such that our wave is propagating in the z direction for simplicity. Then our solution can be written out like h bar mu nu, function of t and z. And this is the A mu nu from before. We get this big matrix where only a few of the entries are non-zero. And I'm going to label them H plus and H cross because they correspond to the polarization of the gravitational wave. And that's what we call those polarizations. Okay. And we can see pretty easily that this matrix is traceless, right? Because if we add plus H plus and minus H plus, that's going to be zero. Cool. So these are the two polarizations of gravitational waves in GR. The common way that we try and understand like how these are distorting the spacetime is by taking a ring of test particles, right? And we assume that the wave is propagating perpendicularly through that ring. So it's either going into the page or out of the page in this diagram, it doesn't matter which. And your ring of test particles is going to oscillate like this. I think it's maybe a little bit easier to see this in an actual animation. So let's do that. And assuming everything works flawlessly. Cool. Okay. All of these links will be at the back of the notes, so you can go here later. Myself and a team of volunteers put together an animation of all of the different possible polarizations including those in modified theories of gravity. So I'll just show you the ones that are true in GR. So if we look at, say, the plus polarization from the front, that looks something like that in motion. This is why we call it the plus mode, because it looks like a plus symbol, right? Here we're actually looking at a tube of all of these rings stacked together, where the red circle in the middle is actually a red arrow showing the direction of propagation, so that if you want to look at them from the side, you can kind of see how that wave is propagating down the tube. Okay. And if we look at the cross mode from the front, we can see that this looks exactly the same as the plus mode, except rotated by 45 degrees about the axis of propagation. Cool. Okay. Yeah.
This is from your VR.
Yeah.
Right? So what set to visualize these in the process, like
Oh, we have the MetaQuest headsets. Yes, yes. We use the MetaQuest headsets. This is part of a virtual reality animation. So you can go in the headset and you can select which polarization you want to be on. You can select different combinations of polarizations and you can see how they all work together to affect the spacetime, which is cool because when you get to adding 6 polarizations together, it's really wonky. And I would never be able to picture that without a little bit of help personally. Okay. Yeah, so feel free to check those out. We'll talk about other polarizations a little bit more next week. Yeah.
You figured it out, pure plus and pure cross.
Yeah.
So I know that the pure, just one of those nodes, right? The points in between the two, like nodes of oscillation, should be completely stationary. So,
Let's go back to the animation so we can actually see what we're talking about. Yeah, they're not completely stationary. They're all moving a little bit depending on where they are on that XY grid. There are equations for this in Poisson and Will. I believe it's we took the ones from chapter 13 because we were using beyond GR polarizations as well, but they have a nice little box in chapter 13 where they write out like X of t is equal to X naught times the amplitude of the gravitational wave plus Y naught. So like the initial X position is initial Y position times the amplitude of the gravitational wave. I think that's a good place to look for it.
and
Yeah, yeah. There are certain like symmetry points where if you were to look at this in like an L-shaped gravitational wave detector, you wouldn't always be able to tell that it's moving because you need a difference in the length of the arms, right, to be able to measure something. So that kind of can confuse the picture, but I think all of these points depend a little bit. Yeah. Okay. So we've predicted gravitational waves from the Einstein field equations. What can source these gravitational waves? Well, let's consider a distribution of mass and energy over some volume V. The mass energy density is given by rho of r at each location, r, and I'm going to expand rho of r out with multipole moments. So the monopole looks like this. We're integrating over that whole volume, our rho of r d cubed r, and that's just going to be the total mass, right? So if we ask ourselves, is it conserved? The answer is yes, because we have conservation of total mass energy. So can this give us any radiation? No, it's conserved. There's nothing time varying here. Okay, so that must not be where the gravitational wave radiation is coming from. If we look at the dipole, that's like this integral over the volume of rho of r times that vector r. So that's like a momentum, right? So is this conserved? Yes. We have conservation of momentum with respect to the center of mass frame. So can we have radiation from this? Correct. No, we can't. At least not in GR. So no dipole radiation in GR. You can have some weird modified theories where you do have dipole radiation because you introduce some sort of preferred frame. But GR. Okay, so we checked the monopole, we checked the dipole, that didn't work. Let's try the quadrupole. So here, same integral, rho of r times ri rj. And is this one conserved? No, this one finally can be varying with time. So is there radiation from this term? Yes, that's the culprit. Okay. And we call the quadrupole moment ij. So we know from this little logical argument that h bar ij must be proportional to time derivatives of iij somehow. All right. Let's figure out how with a sort of Fermi problem style argument. So first of all, gravitational waves are perturbations of spacetime. They must be dimensionless. So whatever we have for our gravitational wave strain should be dimensionless in our geometric units. Also, this radiation carries energy away to infinity. So that's going to give us another piece of info. So we need the luminosity of the gravitational wave to not be zero and not blow up as r goes to infinity. If you remember from some earlier physics classes, for a wave, energy goes like the amplitude squared. It's simple. It's proportional to. Okay. And the flux is equal to the energy per area per time. So that's going to go like the energy, or also like amplitude squared. Luminosity is like flux times area, because this is the energy per time, right? And so if we're thinking about the luminosity, it's going through a sphere at some radius r. This is like flux times 4 pi r squared. So it's going to be proportional to the amplitude squared times 4 pi r squared. Now, I said before, I don't want this thing to blow up or go to zero as we go to infinity. We want this luminosity to be constant. And so because we have this r squared term here, we're going to need amplitude to go like 1 over r. So the amplitude of gravitational waves goes like 1 over r, or falls off with the distance. Useful thing to remember anyway. I call that 0.1. Okay. And the Ij from before, let's look back at that. So this Ij equal to the integral over the volume of that mass energy distribution rho r times Ri Rj cubed r. And this goes like, oops, ml squared, where m is going to be some characteristic mass of our system. And L is like a characteristic length of the system. That makes sense? Because we've got a mass term and then we've got 2 lengths. Great, cool. So we'll call this 0.2. All right, so together, at box 1 and box 2 imply that H goes like some mass length squared over R, which is a length, but we need H to be dimensionless, right? Still need this to be dimensionless. It's a perturbation of space-time. We're working in geometric units where G equals C equals 1. So in these units, mass, length, and time all have the same units, right? So we can pull out some time units to cancel the units we need to cancel to make this dimensionless. And it turns out we're going to want to take 2 time derivatives. So taking 2 time derivatives is going to pull out this sort of 1 over t squared, where t is some characteristic time scale of our system. All right, so all of that together means that Hij goes like 1 over r d squared dt squared Iij. Cool. So we still have some factors of G and C to add in if we want to switch to old SI units, but otherwise we're good to go. This is dimensionless in geometric units. Okay. So we know we need something with a time varying quadrupole moment. What systems have a time varying quadrupole moment? Well, Steve made an animation of some of these for the summer school. So if we click on this, we can go check them out. I would encourage you to look at them more on your own. I'm not going to go through all of them. I just want to bring this up so you can see it. It shows you the monopole moment, the dipole moment, and the quadrupole moment for every one of these different systems. And you can sort of play around with them. But one of the systems that does work and has a varying quadrupole moment is an orbit. Cool. Okay. So that's what we're going to work with now, what we're going to look at now. So let's look at that example, a binary system in a circular orbit. I'll label these M1, M2, and we'll assume that that circular orbit has a radius of r. Okay. A little bit more math. We're almost done. So we'll assume circular orbit for simplicity, but you could, of course, generalize this. It just gets a lot more complicated when you add an eccentricity, so we'll leave that for now. All right, the characteristic mass of this system is going to be the reduced mass. So this is like mu equals M1, M2 over M1 plus M2. This has the right units of mass. It's also symmetric in M1 and M2. So this is what we're going to work with for the moment. Now, if M1 equals M2 equals, we'll call it M, then mu just reduces to M. Right, because then these M's are the same. We have 2M over 2M. Sorry, M squared over 2M. There we go. It just goes to M. Okay. The characteristic length scale of this problem is the semi-major axis. But for a circular orbit, this is just the radius, r. The time variation in this system comes from the orbit, right? So time derivatives are going to pull out the orbital frequency. And then finally, let's call d the distance to the source so we don't get that confused with the radius. Okay, putting all of these together with what we said earlier about gravitational waves, where they go like 1 over the distance times the mass length squared over the time squared. This is going to be like m r squared f orbital squared over d. Okay. Thinking back to earlier physics classes, we can use Kepler's third law, which remember tells us that the orbital frequency squared times the radius cubed proportional to the mass. From that, we can rewrite the radius in terms of the mass and the orbital frequency. So I can plug that back into my expression for h. It's the 2/3 now. Okay, and then that means that H goes like M to the 5/3 F, oh, better write fast. F orbital to the 2/3 over D. These scalings are really useful to know, and I think it's good to know how to get to them quickly through this kind of logical argument. It might be worth studying in case you're prepping for like a thesis defense. These are the kinds of questions advisors like to ask, right? All right, so let's see what this looks like for a couple real numbers. Steve made another nice animation of this. I want to particularly draw our attention to the scale of H. We won't play around with this for long, but okay. Cool. So here with this little web applet, we can, which doesn't work very well on an iPad. Come on. Okay. Oh, great. You can look at those different components, each of those different components. Here we're using the chirp mass as the characteristic mass, just because it's an easier quantity to measure in terms of gravitational waves. So that's great. We'll work with that. The orbital frequency again, and the distance. Cool. And you can sort of play around with these. Oh, it is really not working well on an iPad. Maybe if we use the pencil. There, okay. Great, so you can change these different properties of the system and see how the strain changes. This is strain at the observer on the bottom, and it's really tiny on the screen. It's a little hard for you to read, but you can see that for a system like this, where we have a chirp mass of roughly 30 solar masses at 10 millihertz orbital frequency and at 900 kiloparsecs away, our strain is on the order of 10 to the minus 21. So tiny, very, very, very tiny. And that's going to play into how we measure these things with gravitational wave detectors, which I'm sure will be covered more in the next lecture. Another fun thing that you can do with this applet is you can try different systems and see how systems with different orbital frequencies will appear in different detectors. Down here at the bottom, it's shown. Cool. Okay. Let's go back to the notes. We're almost done. All right. Cool. So from this, we can see how the gravitational waves scale. The more massive your system, the louder your signal is going to be. The farther away your system, this goes like 1 over D, right? So the farther away your system, the quieter the gravitational wave. And we can also see how this goes with the frequency. Gravitational waves are going to carry energy and angular momentum away from the system. We describe this with the energy balance law. So the change in energy over time, dE dt, is actually equal to minus the luminosity of the gravitational waves. Like I said, we call this the energy balance law. All right. So because the waves are carrying energy and angular momentum away from the system, this will cause the orbit to shrink and circularize. So if you had something that was highly eccentric, it's going to tend to a more circular orbit over time. This means that objects will in-spiral, sort of fall towards each other, and will eventually merge. Now, the frequency of the orbit increases as the separation shrinks. Because remember, we have this relation up here. So frequency increases as separation shrinks. And this means that the gravitational waves are going to chirp, right? The frequency increases over time. Think of this kind of sound. All right, This picture is here because this orbital decay prediction was first confirmed by Hulse and Taylor for a binary pulsar. Okay, so this orbital decay prediction first confirmed Hulse and Taylor back in the 70s. They measured binary pulsar system B191316. This was the first ever indirect evidence of gravitational waves. And it was also a fantastic test of GR. Because as you can see from the plot on the right, when we look at the actual data points over 30 years, they line up beautifully with the general relativity prediction for how much that orbit is going to decay as gravitational waves and GR carry energy away from the system. So this won them the 1993 Nobel Prize. All right. Later, gravitational waves were seen directly in LIGO. LIGO being the Laser Interferometer Gravitational Wave Observatory, and that won the 2017 Nobel Prize. All right, let's talk a little bit more about that signal in LIGO. So that first event in LIGO was called GW 150914. These events are labeled for their year, 2015, the month was September, and the day, the 14th. So that's kind of cool. You can always see the date in the label. Now, as we're getting more and more detections in LVK, and there's some risk of them starting to overlap, they've added like the seconds on to the end, and then the names get crazy large and unwieldy, but it's kind of cool. You can tell exactly when they happen just from the name. So here's a plot of the strain data for that first event. These were two roughly 30 solar mass black holes merging about 400 megaparsecs away. And similar to what we were looking at before, the strain is on the order of 10 to the minus 21. It's one of the reasons it took us basically 100 years to measure these things, because we needed the technology to catch up. The LVK detectors are so sensitive that they can tell whether the mirrors have moved to within 1/10,000th the width of a proton. It's just mind-blowing. It's very, very cool that we're able to develop technology that can do that. So here is the strain in the Hanford detector in orange and the strain in the Livingston detector in blue. To be able to pull this really tiny signal out of the data, we need to be able to model it well. So on top in black is one particular model for the gravitational wave strain. This one is IMR Phenom D. Phenom because it's a phenomenological model where we stitch multiple things together for the different pieces of the waveform. So really briefly, just a little bit of like anatomy of a gravitational wave. First, we have this in spiral portion, right? And this is really long, where the binary starts out kind of widely separated and is in spiraling in. So in this portion of the signal, the speeds are slow, or at least slow relative to the speed of light. And gravity is at least relatively weak enough that we can use a post-Newtonian expansion. So we can use post-Newtonian approximations to calculate the strain analytically. Right? Once those objects get close enough, they merge, and then the final product will ring down. This is as the system returns to equilibrium, right? And so here in the ring down portion, we can model the remnant with black hole perturbation theory. So again, in this portion, we can calculate strain analytically, but we do it in a different way than in the first portion. And then finally, in the merger here, when these objects are actually colliding, we have such strong gravity and like really dynamical fields. Things are happening very fast. So we can't solve this analytically anymore. Here we have strong gravity. It's highly dynamical. So we need numerical relativity. Okay, and at least in LVK where we're actually seeing the merger, some detectors will see portions of the in spiral, right? Other detectors will see like the merger for a particular system. At least in LVK where we're seeing portions of the in spiral merger and ring down, we stitch all of these techniques together to get one phenomenological waveform that we use to search the data. So once we have a model for the gravitational waves, we can work on actually detecting them, which will be the subject of basically the rest of this workshop. So I'm gonna leave it there. Yeah. Any questions? Yeah.
You mentioned the problem of being proportional to the characteristic mass of the plane. Is there an expression for that characteristic plane that we can derive from what we've done so far?
Would you mind repeating the question just so we all catch?
Oh, yeah. So I mentioned that the question was, I mentioned that the quadrupole moment was proportional to the characteristic mass times the characteristic length squared. And the question was, is there any like way to justify what the characteristic length should be?
Yeah.
Well, I mean, you can go through this calculation very carefully for a binary system and like do all of the math out exactly. This is sort of a hand wavy logical argument way to get there, where the only length scale that really could matter is how far apart they are. So it's going to be in some way proportional to the radius. Maybe there's a factor of 2 in there, but I don't care. I was using twiddle math all the way through. Yeah.
Why we need that higher for hitting gravitational wave.
Yeah.
Something to do with the, so for instance, in terms of the transverse age requirements on radiation, just.
Why we need a time varying
Yeah.
quadrupole moment. Okay, let me repeat the question. So the question was, why do we need a time varying quadrupole moment? So
Going back and back.
Mhm.
Where
Like-
is that?
like in here where we're getting, we need 2 time derivatives. Want to go through here? Does that work? Because in this case, like we have ML squared over an L, right? So we have basically 2 units of length on top that we need to cancel. So we throw in 2 units of time in the bottom, which we can pull out with time derivatives.
They got that.
Okay.
Yeah, I think even to get to the point where you've got the second time derivative.
Mhm.
There's more math in there than going from just like the linearized field equations.
Yes.
That it's related to the edges of expression for the flux and gravitational waves. So there's probably.
Yeah.
If you build it offline as well.
Yes. We're skipping a lot of steps to try to do this in 90 minutes. This could be the content of several lectures. There's a good walkthrough of how to do this specifically for binary again in Poisson and Will. I think it's chapter 11. They do this really carefully.
It is sort of like a very generalized continuity equation. So where you have the source on the right, so like.
One sort of really nice pedagogical paper by Bernard Schutz called Gravitational Waves in the Background. And there's very little math in it, but he makes the relationship between gravitational waves and electromagnetic waves
So if you think about how you generate electromagnetic waves, you take an electron, just shake it.
Right.
And that accelerates it, and generates electromagnetic waves. And the same is true of the gravitational waves here. The only difference really is that electromagnetic waves are sourced by, leading over dipoles, where gravitational waves are particle moments, but you need to shake the charge each year as it passes.
I think the Anderson University can be able to also like basic equation also there like how the frequency of with the frequency and issue. The Anderson is also scanning able to also get the frequency equation.
I'm sorry, I'm having a hard time hearing you. Um, the animations that Steve made, can we observe the frequency of? Oh, can you observe them evolving over time? I don't think so. I think it's just at like one sort of stationary point, but Steve would be able to answer that better than I can.
That's the animation should be an option to switch on and start on.
Oh, here we go. Beautiful.
And then that is actually using the leading order evolutionary equations, here's things, four equations for the moment eventually it does merge. And then the ring down modes are.
Yeah, that's fun. And so if we were to pick something that was like starting at a much lower frequency, here we go. They won't let me start it at a different spot. Oh, maybe if we go here. If we start it much slower, then the inspire will take forever. Maybe it's sped up in here, but yeah. If you start at a low enough frequency, it takes a really long time. Cool. I'm also happy to chat with people after during break. Yeah.
So you said that, the dipole cannot source gravitational radiation in GR?
Yes.
But down to what did that?
Yeah, okay, the question was in what, so we said that in GR, the dipole moment doesn't source gravitational radiation, but that there may be some cases where you have modified theories where you can get a dipole gravitational wave. So in what cases would that happen? One particular example is called Einstein ether theory. This is a very strange theory where you have an additional vector field everywhere in your spacetime. And this means that there's now a preferred frame. And so once you have that preferred frame, now you can have some like motion with respect to the frame. And that's what's going to make this dipole moment no longer conserved. And you can have a dipole term in your gravitational radiation. Yeah, good question. Cool. Okay, I think, oh, sorry, Levi, do you want to ask one?
I think it's sort of in that period and the.
Yeah.
Must be really, really small, right?
Yes, because it's supremely well constrained by other experiments. Yeah, the question was, is that dipole radiation really, really small? And yes, it has to be crazy small, because we've already done a lot of experiments that show that the dipole, any dipole radiation would have to be very, very tiny. So the coupling constants of this theory are fairly well constrained, but there's still some space where they may not be. It's a strange theory because you have 4 additional coupling constants, and a lot of the functions that matter for the theory are actually like ratios of those coupling constants. So you can have something where the coupling constants are large, but the ratio is small, and play those kinds of games. That's a topic for next week. Yeah, cool. All right. Thanks, guys, for that. Let's break.
That was great. Thank you very much, Kristen. So we have a break for about 15 minutes now. Help yourselves to any snacks that are left in the back of the room there. If you're in need of coffee and there's none in the out, you can also go across the hallway to get them to get proper coffee. They have espresso and whatnot. I think we'll come back at 11:15 for a discussion about application. Okay. Thank you.
And they're all work out really well.
Yeah, it's a repository, literally a repository. Yeah.
So you.
Yeah, because your family, I'm just like physically counted, doing mostly with Irina, hopefully I want to mention that I can do that.
I just thought I hope that the brand new. That's so very. Yeah, I'm sorry, yeah, that's the. One more. What was on it? Yeah, so it would be good that. So good. I should be a rule of my heart. So I think the interesting questions. That's what I would be able to. Yeah. Okay, and then just follow the back.
Okay. You just need to. Challenge to it, really information. We're showing. I'm showing my best.
And if you have like a circular, you want to share your coordinate.
Right. The whole thing not understand. Right, it's not like it's not like. We're. Every time our overlap should push you into a different part of it. whole space. Maybe it's very more, it would be better with that part. Right, because the whole thing is down here. So when you think about the soccer and doing headmasters has some around. Yes.
Yeah.
Mm.
People say
So. Maybe that's what it was.
Yeah, okay, that's about that. I was thinking of the conference that we have.
Right.
Can stretch everything, you know, right, it's the whole thing, yes. And then you have to break up what you're saying.
Well, yeah, anyway, kind of, I'm looking for.
I was very pretty sad. Really, that's what this thing got another. How would I know? In order to get a part of move. She doesn't have history. No. It's just. This thing out, maybe this. All fine. Sure.
I didn't put it, I said, no, but this, somebody has, like, an example, they would have way, you don't believe that it's funny, things has. I mean, you're like, how was it? Yeah, that's how it goes. So if they get you. No, it's true. Never, not.
It's fair to use that, because I mean. In a little way, that's what it is, yeah, exactly, right, and so we have to do this relationship and right, here it was. I'll leave it out.
Yeah.
That's really, perfect. I mean, I think I like this one, we can't review. Yeah.
I think we'll just keep it. We're constantly streaming on this. We're also on YouTube, and this one's connected on there, so.
It gives me a lot of opportunity for you guys to say. Yeah. Oh, yes. So when we're talking about what is it you're asking? Yeah. Yes. Everybody's here with problems. Okay, so you'll do some problem that you'll think that's about time. It's a whole stage. So it's so sure. Yeah. How long do you I'm going to get out. That's all. Really going okay. Maybe excited. Start. I He's saying
There's a Zoom update that has broken my Zoom.
Oh, no.
So great. Very weirdly.
Right, you already want to go.
Are they carrying? Are they just trying to get?
Okay, careful.
Association very. Right? Yeah, whole time. Yes, yes, that's a long, it's like, yes. Well, that's it. So for the. Yeah, oh, it's definitely, yeah. Yeah, so, yeah, I think it's. Yes. Yeah, yeah. So, yeah. Yeah, it's, yeah, sometimes you're right. Yeah.
Is there a special organizer leadership to the line? Yes. Can you give me a share motion instead?
Yeah.
Share options. No, they don't. It's a button to share. Very strange.
Kristen was able to share his.
Oh, good.
You know, I mean, the marching hand, I did, that's the 106 days. Yeah, yeah. There was, that is the football, like, match you can handle.
I don't have a video.
If you want, instead, you could email the.
It's just
yourself and-
both sides. Let's just do that.
Oh, we are muted, so.
You did?
Thank you for doing this again.
Oh, absolutely.
Very well.
Yep. Should be.
All right, everyone, let's take seats again for the second lecture. Alexander Criswell, he's a local postdoc, expert on LISA and alternative arrays. We're going to talk about gravitational wave detectors across the spectrum.
Everybody, thank you to Steve for the introduction. I'm going to be talking to you today about how we do gravitational wave detection, not just in pulsar timing arrays, but across the entire spectrum of gravitational wave science. And what you can expect from that, I'm going to give you a basic primer on how we detect gravitational waves in the first place, what the different sources are that we can see across the entire gravitational wave spectrum, and give you a history of the field, walking through all of the different efforts to detect gravitational waves, both successful and unsuccessful over the years. Give you an overview of current GW detection efforts and sources of interest, and then we'll start to explore more farther out concepts across the entire spectrum for future missions and detectors. Okay, so I expect that all of you are familiar with the electromagnetic spectrum, where we have, since Galileo invented the telescope way back when, in the optical, we have slowly and then extremely rapidly expanded our ability to detect electromagnetic radiation across an entire spectrum of light, ranging from the radio all the way up to the gamma rays at very high energies. Now, just like in electromagnetic radiation, where the wavelength of the light that is being emitted is directly connected to the energy of the photons involved and the nature of the physical processes that are producing that light, we can make the exact same kind of statement about gravitational waves. When we're looking at gravitational waves, we're going to be looking all the way from generally kilohertz frequencies at the high end down through nanohertz and below at the low end. And the way that you can really think about this is that as you move to higher gravitational wave frequencies, you are moving towards smaller masses and shorter timescales. Whereas when you are moving towards lower gravitational wave frequencies, you're moving towards more massive things that happen on larger physical scales. So we can see this in the sort of rogues gallery of sources that we have across the entire spectrum. So down in the nanohertz, we're looking at supermassive binary black holes, really, really big objects happening on sub-parsec scales. Whereas if we move all the way up to the kilohertz, we're looking at compact binary mergers, which are things like neutron stars the size of New York City, or stellar mass binary black holes, which are even smaller in terms of their event horizon, that are merging together on the orders of seconds. In the middle, we have the millihertz band, where you have systems that are either stellar mass binaries that are far from merger, orbiting at periods of minutes to hours. You have massive black hole binaries, which is pretty loosely defined. Basically, anything that's going to be happening in around an hour or minute sort of time scale is going to then emit gravitational waves in the millihertz. And this corresponds to masses that are of middling size, or systems like on the top, which is an extreme mass ratio inspiral of a compact stellar mass black hole, for example, inspiraling into a supermassive black hole. So by looking at different parts of the gravitational wave spectrum, we can probe different physical scales and get insights in different kinds of astrophysics. In the kilohertz, where we're doing what we'll see is terrestrial gravitational wave detection, we can start to probe very fine tests of GR. We can start to look at the nature of neutron stars and the equation of state of dense nuclear matter. Whereas all the way down on the nanohertz side, since we're dealing with supermassive black hole binaries, we're probing the formation and evolution of those systems, galactic evolution, these sorts of things. So how do we actually detect any of this? I understand you've been given an excellent primer on the theory of gravitational waves more broadly. And when it comes down to actually detecting them, this is the main quantity, so the strain h, right? And when we observe that in practice, what we're looking for is a change in length over a length. As the gravitational wave passes through, as you were introduced to, it's going to stretch and squeeze space-time as it propagates. And so if you have for example, a photon that is propagating through space-time and a gravitational wave passes through, those photons will take a little bit longer to arrive, and then a little bit shorter to arrive, and then a little bit longer to arrive. And this will be imprinted into the four-dimensional space-time. Now, the problem with doing any kind of gravitational wave detection, and the reason that for a very long time it was thought to be completely impractical, is that strain, this amount that space-time is being shifted relative to its state when it is when there's no gravitational wave present, is very, very, very small. For gravitational waves that are emitted in the LIGO, and we'll talk more about LIGO later, but in the terrestrial gravitational wave band, we're looking at 1 part in 10 to the 21st. This is equivalent to me plucking a single hair off of my head, putting it next to this room, and then scaling this room down to the size of a proton, the hair along with it, and that's the amount of change that we're trying to detect in terms of the overall length. So in order to do this, you need one of two things, and ideally both. You need to either be able to very, very, very precisely measure a change in distance at the sort of 10 to the negative 21st level of precision, or you need a really, really, really big length that you're sending photons back and forth over, so that a small fraction of a big length doesn't require all that much precision. And in practice, we're going to have some combination of these two things. The other effect of scaling the size of our observatory is not just allowing us to not have quite as much sensitivity and still be able to detect a certain amount of gravitational wave strain, but it's also going to impact the frequencies that of gravitational wave radiation that we can actually access. So if you have a very large observatory, you're going to be able to observe gravitational waves with wavelengths that are roughly proximate to the size of your observatory. So if you have a LIGO-like observatory that has arm lengths of, say, 4 kilometers, you're going to have access to hertz to kilohertz gravitational waves. If you, as we will see, have a pulsar timing array with arm lengths of size of the galaxy, you're going to have access to gravitational waves that have wavelengths of order the size of the galaxy. Okay, so going back to 1916 is when we get Einstein proposing his theory of general relativity, and specifically noting that gravitational wave radiation is a consequence of his theory. He actually goes back and forth over the course of his life as to whether or not he believes that gravitational waves are a real physical thing that can happen, or if they are simply a consequence of the mathematics that's an oddity and wouldn't be found in reality. People started thinking about this for a long time. There are many arguments over whether or not these things are real or not. And eventually, having sufficiently convinced themselves that gravitational waves have to be a real phenomenon, although possibly completely impossible to detect, people started developing ways that they could actually try to detect these things. And so in the 60s, two Russian scientists, Gerstenstein and Pustovoit, and Ray Weiss and company, independently in the US and in Russia, because we weren't talking to each other all that much at the time, proposed the concept of interferometric detection. And the idea here is that you use a thing called a Michelson interferometer, which is being displayed up on the screen right now, in order to get the level of precision that you need to be able to detect gravitational waves. And so the idea is that if you have a interferometer consisting of 2 laser beams and a beam splitter, where I'll keep this going. 2 laser beams and a beam splitter, where you know very precisely that the arm lengths of each of these 2 long laser beams should be exactly the same size in their rest state. And you can confirm that by sending the light down to one end of each arm, having it reflect, come all the way back, get recombined at the beam splitter, and if your lengths are precisely equal, you will have perfect destructive interference. No light will come out the other side. But if a gravitational wave passes through and slightly stretches your observatory along one axis and slightly squeezes it along the other, and then does that back and forth, you're going to see dephasing of the laser beams. So they will no longer perfectly combine with destructive interference, but instead you see that there is some laser light actually getting to your detector, and that flashing is how you actually detect the gravitational wave in the end. Now, the technology was not ready for interferometric observatories in the 60s. What could happen was a resonant bar detector. And the idea here was quite far from interferometry. It was instead, if you build a cylinder of a very particular length and you completely isolate it, if a gravitational wave passes through that has the exact frequency that you have tuned this cylinder to be resonant to, just in a like mechanics and like a graduate mechanics sense, right? Your bar detector should start vibrating on its own. The gravitational wave should couple with the detector and incite a resonant vibration. A man called Joseph Weber pioneered the concept of resonant bar detection. They were called Weber bars. In 1969, he claimed that he had a gravitational wave detection in multiple of his bars. Unfortunately, his results were never able to be reproduced, including by coexisting and more sensitive resonant bar detectors that were present at the time in Europe. And when folks went back and analyzed the data, if you look at the strength of the signal that he reported to see, the amount of energy that it had to contain, were it in fact a gravitational wave signal and not just something else managing to shake the detector, would be completely unphysical for any astrophysical source that we know of. So he was a pioneer in the field. He never ceded the fact that he hadn't detected gravitational waves and kept trying to detect them until he passed away. And so he's remembered as a sort of a mixed figure in the field, but you really do have to recognize the fundamental contributions that he made to the foundations of the field, and he frankly built the first gravitational wave detector to ever exist. This did leave the field in a somewhat tricky spot in that these unfortunately incorrect claims of detection had been made, and so the bar for getting it right had been raised actually quite a bit. There was an attitude within the field that if we had another occurrence like this of especially a large collaboration claiming detection of a signal that was later proved to be a false detection, that it would damage the reputation of the field so irrevocably that people would stop investing in it, essentially. So if you find that especially a lot of senior faculty are very, very, very careful and very cautious about whether or not they want to claim detection, even though now we know gravitational waves are real, spoilers, we detected them, that's where that caution comes from, is many decades of needing to be absolutely certain if they were going to make a claim like Weber did, because we couldn't afford to get it wrong again. Fortunately, in 1978, there was the first indirect detection of gravitational waves in something called the Hulse-Taylor binary. So this is a binary system in which one of the members was a pulsar, and Hulse and Taylor were timing the pulsar very precisely. And they were able to note that the orbital period of the pulsar was decaying over time. And so what you see in the black line there is the prediction from general relativity for the masses that they had measured of the system, of the orbital decay of the system, and the reduction in the period as the two members of the binary got closer and closer together due to the emission of gravitational wave radiation extracting energy from the system. And in red is the measurements that Hulse and Taylor made of this binary's orbital period over time. And obviously, as you can see, it perfectly matches the expectation from general relativity. So this was broadly considered a confirmation of the fact that gravitational waves exist and are not just some spurious mathematical feature of general relativity, but they are an actual, real physical phenomenon. And Hulse and Taylor won a Nobel Prize for this some years later. Burgeoned by the energy in the field after confirmation that this thing that we've been talking about looking for actually does exist, a number of people in the US were able to convince the US government to give them some money to found the Laser Interferometer Gravitational Observatory, or LIGO, which would be an interferometric detector of the kind that had been proposed about a decade previously. Shortly after that, the Laser Interferometer Space Antenna, or LISA, was proposed. The idea of, okay, we're realizing that it's going to be very, very hard to get the level of precision that we need on the ground, because anything that we build on Earth is going to be connected to an entire planet that moves around a lot. And so the amount of seismic noise that you have to deal with is very, very difficult. And so starting with Pete Bender and some colleagues, the concept that would become LISA was proposed of, okay, we'll just put it in space. We'll make 3 satellites, we'll send laser beams in between them, and we'll see if we can detect gravitational waves that way. And I'll return to more on that later. In 2001, after 16 years of construction efforts, initial LIGO began operations. They were not expecting to detect any gravitational waves. The intent of the observatory was to have a proof of concept that the technology actually worked and that they could get a good ways towards the sensitivity that they thought they needed to in order to detect gravitational waves from binary black holes or binary neutron stars merging together. And it was overall a success in terms of the experiment itself, although of course it did not detect any gravitational waves at the time. In 2005, Nanograv began its pulsar timing observations, and again, more on that later. 2014, all the while, LIGO has been upgrading and trying to get more and more and more and more sensitive. But in 2014, another false alarm detection claim was made by Cosmic Microwave Background Observation Collaboration by SET2. So the idea here is that if you have very, very, very large scale gravitational waves, well, I guess technically at the time they're very small, but if you look on very, very large scales, you can see primordial gravitational waves from the early universe during inflation. And the theory is that at the time, you should leave an imprint on what is called the B modes of the polarization of the cosmic microwave background. And these would be an indicator of primordial gravitational wave radiation in the early universe that has now been blown up and so redshifted by the expansion of the universe and by inflation that it exists at extremely low frequencies, 10 to the negative 14th hertz. And BICEP had been imaging for this for a long time. They saw and they confirmed what they thought were cosmological B modes in the cosmic microwave background. They released a detection, and a year later, when combining with another major cosmic microwave background observation experiment, it was found that galactic dust had made a spurious signal that they had not considered in their analysis, and this killed the detection. Fortunately, before any funding could get pulled, later in 2015, LIGO observed the first direct detection of gravitational waves with a system called GW 150914. Those phone numbers there are going to be year, month, day. So 150914 was observed on 2015, September 14th. Now we also append a whole bunch of other numbers for the timestamp, because when we came up with this particular notation, we hadn't considered the fact that eventually we might detect multiple gravitational wave signals in a day. But that's where we are now. 10 years later, and we have the 5th gravitational wave transient catalog, which consists of hundreds of systems. You can see that over time, oh, why is this saying set up professional audio? Get rid of this. Great. Okay, you can see that over time, we've accrued many, many more signals. That 01 label there, those first 3 spectrograms, and each of these are the actual strain spectrogram from the LIGO data. X-axis is time, y-axis is frequency. We saw 3 systems merge, GW 150914, and then 2 others. In the second observing campaign of LIGO and Virgo, we saw, I believe, another 8 systems for a total of 10. And then the third observing run, more than, I think, quadrupled or quintupled that. And then the entire rest of the plot, O4A and O4B there, are the systems that we have observed in the last LDK observing run that ended just this spring. So that was a year and a half of observations. 01 was also about a year and a half of observations. We have gotten much more efficient at detecting these things as we've created a more and more and more sensitive detector over upgrades. And what we've seen is actually a fantastic surprise to all of the theorists before LIGO detected the first system. Because what we were expecting at the time is that we would get a few binary black hole mergers, but they would be fairly rare, and we would be swamped. We would be awash in binary neutron star mergers. They were expected to be the most common source that LIGO would detect, full stop, period. And this is why you always have to listen to theories with a grain of salt and plug them into your observations and see what you actually see, because there's been a massive amount of science that has been unveiled by the fact that actually what LIGO has mostly seen is binary black hole mergers. We've gotten 2, maybe 3, 2.5 binary neutron star mergers in the entire decade that we have been successfully observing for gravitational wave signals. And we've managed to see binary black hole mergers from across the entire mass range that we expect from stellar mass systems, and actually quite a few for masses that we think can't form in stellar binaries, which is the current mystery of there's supposed to be a big old mass gap in here, at which point you can no longer form a black hole from a core collapse of a massive star, and I don't see any mass gap. We're even starting to detect systems that we didn't even think existed up at some hundreds of solar masses. I do have to take a step back just to highlight that this graphic is made by Ryan Nowicki, who is a grad student here at Vanderbilt, and made a really, really fantastic display of all of the signals.
Super sorry to interrupt your flow, but
Yes.
our timing of logistics is a bit off today.
Okay.
It's day one. Is it possible we can take a pause for 15 minutes since there's pizza at the back of the room?
Perfect.
Maybe people can get pizza, grab their lunch, and then 15 minutes we come back and I'll down here, maybe we can talk about detectors.
Yeah.
So we'll just take a quick pause, quick intermission. Let's grab pizza back of the room and then we'll continue.
Yeah, sounds like a plan. I could eat.
One quick question. Is it possible by neutron star because of astrophysics?
Okay, folks, Alexander turns.
All right, part two. Get rid of this. And that. All right, perfect. Okay, where were we? We were looking at the set of gravitational wave observations that have been made by LIGO, Virgo, and Kagra using laser interferometry to observe mostly binary black hole mergers, but also some binary neutron star mergers and neutron star black hole binary mergers. So this is, broadly speaking, what we have seen over the last decade. This is a fresh plot. The catalog for GWTC 5 was released about a month ago. Excuse me. Okay. And again, what we've managed to see with this has been really startling is the wrong word, but really surprising in terms of what we were expecting to see. This includes systems spread across regions of mass that we didn't expect there to be systems in at all. This has been observations of black holes that are larger than anything we think can be made by a star, full stop. And this has included a relative dearth of binary neutron star mergers. So in 2017, so about 2 years after the first observation of gravitational waves from a binary black hole merger, we saw GW170817, so that was on August 17th of 2017, which was a binary neutron star merger. It was observed in gravitational waves. About 2 seconds later, Fermi GBM saw a gamma ray burst that had a localization coincident with the gravitational wave localization at the time. Almost every telescope on Earth that could observe the gravitational wave and Fermi GBM localization slewed their telescopes to it. And we found a transient counterpart, AT, so astronomical transient 2017 GFO, which was a kilonova. So this was the near-infrared optical UV counterpart to the binary neutron star merger, a shell of expanding matter that was thrown off by the two neutron stars as they were merging together. This solved a host of mysteries, including where did all of our heavy elements come from, because we can't make the abundance of heavy elements that we see in the universe by just supernovae. We need some sort of other mechanism. A number of them had been proposed, including binary neutron star mergers, and we were able to observe the rapid nucleosynthesis in this expanding optical and UV transient counterpart as a site of this heavy element formation. Now, unfortunately, so this was about, I guess, 2 years before I started my PhD. I went in at the time, we were all jazzed. We've been observing for 2 years. We had already seen a binary neutron star merger. It was 40 megaparsecs away, which is very close in terms of gravitational wave mergers. We're going to see a whole pile of these. We're going to be able to do all this cool science. It's going to be an era of multi-messenger discovery. Then we saw one really massive binary neutron star merger in 2021. And that's been it. So I don't work on binary neutron stars anymore. Really fantastic potential for science. We will get there eventually. But it seems that the rate of binary neutron star mergers is much, much, much lower than we were expecting going into LIGO observations. And we still haven't really figured out why. On top of that, we have no longer solved where all the heavy elements in the universe come from. Because with a binary neutron star merger rate this low, having not seen another one or seen exactly one more for almost a decade, we can't make all of the heavy elements in the universe that we observe with just supernovae and kilonovae. So where do they come from? We don't know. Maybe you'll find out. So right now, as we stand, the LIGO Virgo Kagra group of collaborations has finished their fourth observing run, 04, which ran from, oh gosh. I don't remember when it started. It was long enough ago that I don't remember when it started. About 2 years ago, I think now. Their fourth observing run, which lasted about a year and a half, 2 years, consisted of the 2 LIGO detectors. There's one in Livingston, sometimes called LLO, one in Hanford, LHO for LIGO Hanford Observatory, and the other one respectively. There is the Virgo detector, which is in Italy near Pisa, and then the Kager detector, which is near the Kamiokande mine in Japan. Currently under construction is LIGO India, which is expected to be online in hopefully the early 2030s. It's actually moving along at a fair clip now, so we're excited for that to come online. It's expected to take much less time to actually construct than the original LIGO observatories, in part because we've gotten very good at this, because we have a bunch, and in part because it's going to be created with a whole pile of essentially spare parts for Livingston and Hanford that have just been shipped overseas, had already been made, no longer needed by those 2 observatories, and so we can just mostly build a third one with those parts. So the real advantage of having a network of gravitational wave detectors is you get some improved science along a number of axes, but at least for me, the major one is sky localization. And you can think about this exactly like triangulation. If you have one detector, well, you have a different problem. If you see something, you have no way of confirming whether or not it was a gravitational wave signal, or if it was loggers driving down the street with a bunch of logs in the back of their truck hitting a bump, a real noise source at LIGO Livingston that is in fact a seasonal modulation in their noise because the logging is seasonal. Or if you've actually seen a gravitational wave signal, right? If you have 2, if you see a trigger in LIGO Livingston and then a trigger in LIGO Hanford, in the exact delay time that it would have taken for the gravitational wave to propagate across the Earth, the distance between those observatories, great. Now you have a good amount of confirmation that you're confident that you've detected a gravitational wave signal, but your inference on where that gravitational wave signal came from is essentially half the sky. And so you'll see these big banana-shaped sky localizations that basically say, well, we saw a binary black hole merger. We think it came from that way, which is deeply unhelpful if you're an electromagnetic astronomer trying to point a telescope at it, because that way is half the sky, and your telescope is this much of the sky. If you add a third detector, you start to get better. It basically localizes it onto a thin ellipse that still stretches over much of the sky. This is actually what happened with 1708-17, that binary neutron star merger, is that it was detected in Hanford and Livingston, and actually, crucially, it wasn't detected in Virgo. And they did the math, and basically it turns out there was only a very, very small region of the sky on which this signal could have happened and Virgo wouldn't have seen it. And so that locked us into a small portion of the sky and allowed us to find the first multi-messenger observation, including gravitational waves. I always have to asterisk that because supernova 1987 was observed in light and neutrinos. So it holds the title of first multi-messenger observation, period. If you start to have multiple additional detectors, though, you start to be able to get localizations down to the size of one of our electromagnetic telescope survey fields, something like the Zoika Transient Facility, ZTF, or the Vera Rubin telescope, which has just started its observations. That provides incredible potential for multi-messenger astronomy. We learned a ton from 1708-17 because we could both get information about it from gravitational waves and from the electromagnetic spectrum. And they provide complementary information. And so we're very, very excited about the prospect of being able to localize even binary black hole mergers down to very, very, very small amounts of the sky to see if they have disks around them that are colliding and flaring. But by the time that you pan a survey across half the sky, you've missed those signals entirely. Okay, that is the current state of terrestrial gravitational wave observations from ground-based detectors. We're now going to take a step back into what you are all here for, which is pulsar timing. And this again goes back to the 70s when figuring out how one might detect gravitational waves was a hot topic. And so Sazin and Detweiler in the 70s proposed the idea of a pulsar timing array that you could see instead of having a very precise laser that you know exactly how long it is and seeing a deviation in that light travel time. What if you say, okay, I've got another source of photons that I can measure very, very, very precisely and that I know a lot about, which is the pulsars in the Milky Way. And you observe those pulsars and you see if those photon arrival times start to differ in a correlated way across your entire array. In 1983, Hellings and Downs showed that you could do a cohesive search for a gravitational wave signal across the entire array, and then it would have a specific angular correlation that's called the Hellings and Downs curve. Sometime later in 2005, Nanograv begins its pulsar timing observations. By 2020, this is a long-term experiment. 15 years later, there are hints of a common process around each of the pulsars in the array, but no way to be sure whether or not this was actually a gravitational wave signal until in 2023, there was a detection of strong evidence for a gravitational wave background in PTAs at something like 3 sigma. At this point, everyone was very confident that they had indeed seen something, but that caution is still there, right? As a field, we're trying to do measurements that are extraordinarily precise for a signal that is extraordinarily weak. And we have to be very, very, very careful. So we got very excited. Frankly, everyone outside of the field has interpreted this as a detection of a gravitational wave background. But really what we've done is we found strong evidence for, and we continue to accrue additional signal. And hopefully in the next couple of years, we'll be able to pass that glorious 5 sigma boundary and 3 people will care because we've been seeing the same gravitational wave signal for a decade at that point. Meanwhile, again, back in the 90s, the Laser Interferometer Space Antenna, or LISA, was proposed. I'm not going to go into all of the gory details of the late 90s and the 2000s in terms of the will they, won't they between LISA and funding agencies in both the United States and Europe. But suffice to say, by 2015, a mission called LISA Pathfinder launches. This is essentially one of the 3 satellites that will eventually make up LISA. It goes phenomenally. The point of LISA Pathfinder was to characterize whether or not the expected noise levels on the LISA satellites were going to be sufficient to actually do gravitational wave detection at the sensitivity that we were claiming. There was a curve for the target sensitivity of LISA, the much higher noise curve for the target sensitivity of LISA Pathfinder, and LISA Pathfinder beat the mission requirements for LISA itself. So after that, everybody has been very confident. And as of last year, LISA has been formally adopted as a joint ESA-NASA mission with a launch date of 2035. So it's going to be 3 satellites in a roughly triangular satellite constellation. It'll be in the same orbit as Earth, about 20 degrees ahead or behind us. And the 3 satellites will essentially tumble over each other in a set of very cool free fall orbits that keeps the constellation in a roughly triangular shape. On each satellite, there will be 2 laser sources and 2 telescopes. Each of these links will be 2 one-way links. So instead of LIGO, where you have to be able to send your laser all the way to the far end of your interferometer, bounce it off a mirror, and come all the way back, when you have LISA, which is instead of LIGO's 4 kilometers on an arm, is 2.5 million kilometers on an arm, it's very, very difficult to do that in any reasonable way. So you have a telescope on each one, you've got 2 two-way links, and then we do something called time delay interferometry to digitally create an interferometer from the 6 links in the satellite constellation. LISA has an embarrassment of riches. The biggest problem with LISA is not the technology, which has been clearly shown to be ready. It's not whether or not gravitational waves exist. They clearly do. It's that LISA will have too many gravitational waves. And this is a real problem that we are struggling with right now. Because the millihertz band, where LISA will be observing, is incredibly source rich. And this is honestly just a consequence of the fact that a lot of things happen at timescales of minutes to hours in the universe. It's a pretty reasonable timescale for things to happen at. And you end up having everything from massive binary black hole mergers to every single close compact stellar binary in the Milky Way. You get systems that are orbiting around and plunging into supermassive black holes as stellar mass signals. You have precursors to LIGO-style signals of compact binary coalescences from, say, a binary black hole merger. But instead, 10, 20 years before that system will merge in the ground-based gravitational wave band. And these are all piled on top of each other. On top of that, you have the collective confusion noise from so many of these signals strewn throughout the universe that are all stacked on top of that. And the effect of it is that we can't see the LISA noise for the gravitational wave signals, and we also can't see the gravitational wave signals for all the other gravitational wave signals. And so the LISA problem is really an analysis problem. It's a software problem, and I'm talking about it extensively. This is what I spend a lot of my time on, is figuring out how we can actually piece apart all of these different systems and actually do the science on what is an effect, something like 30 million gravitational wave sources in a trench coat. And so the thing that has been proposed to deal with this is called the global fit, where we essentially just say, okay, we have enough computational ability. It's 2026, it'll be 2035. We've got all sorts of crazy GPUs, we've got supercomputers. Let's just do it. Let's just fit every single thing simultaneously. 100,000 parameters, maybe more. And we think we can do it. We've come a very, very long way in making this kind of thing happen, and we are tentatively confident that we can actually analyze the data when it comes out in 2037, unless there's something in there that we weren't expecting, in which case we'll all panic and scramble. Yeah. Yeah, so the verification binaries, we're not calling verification binaries anymore. The original idea was that there are white dwarf binaries in the galaxy that we've observed electromagnetically already. And so these are essentially multi-messenger sources. And the idea is that we could take those, and because we can measure their orbital periods, for example, extremely well, get some inferences on their masses and et cetera, that we would know exactly what that signal should look like in the LISA data, and that we could actually use it as a way to characterize the LISA instrumental noise. Turns out that that idea doesn't quite work. And so what we will often call them these days is either known binaries or multi-messenger galactic binaries. But they're going to be really cool science sources. They're just going to be less useful as a instrumental noise monitor than we thought they might be. Okay, I think that's all I wanted to say here. Let's look to the far future. So in the US, there is an ongoing effort called Cosmic Explorer, and a similar effort ongoing in the European Union called the Einstein Telescope. And the idea here is to build the next generation of terrestrial gravitational wave observatories. We're going to take the lessons that we've learned from the current network of gravitational wave detectors on the Earth, and we're going to take those forward into the future, step forward the technology in a really big way that we can't do just via upgrades on our current detector designs. In part, that means making them bigger, right? Going back to one of those first couple slides, you can make your detector more sensitive by making L larger. And so instead of having the 4-kilometer arms that LIGO currently has today, Cosmic Explorer is expected to have either 20 or 40-kilometer arm lengths. This creates some technical problems in terms of building this thing. in part because you can't actually lay a perfectly straight 40-kilometer tube on the surface of the Earth because the Earth is round. And so your two ends will just kind of be wobbling there in midair. So you have to dig some kind of trench to make a perfectly flat 40-kilometer arm. The Einstein telescope concept that's being explored is an underground observatory that's in a triangle configuration like LISA, doing a similar sort of digital interferometry that actually has two different interferometers, one low frequency one and one high frequency one, layered on top of each other in the same structure. And then the idea is that both of these detectors would go forward in parallel so that we can again have a next generation global network of gravitational wave detectors. And the reason that we want to do this is actually a really, really compelling science pitch, which is that we'll get everything. Every single binary black hole merger, stellar mass binary black hole merger, every single binary neutron star merger, every single binary neutron star black hole merger in the entire observable universe, going back in terms of binary black hole mergers to a redshift of 60. This would be an unprecedented view into stellar evolution, star formation, primordial black hole formation across the entire cosmic lifespan. That's really compelling. People are pretty on board with this. The EU government is pretty on board with funding Einstein telescope. The current state of that is they're arguing over who gets to have it. And so it might not actually end up being a triangle that's in one location like this, because if you have two L's in a more LIGO style thing, you can put it in two countries and then two people get to have it. There's a proposal even to have it kind of crossing over a couple borders in Northern Europe, so everybody gets in on the action. In the US, things are going okay. I would say they're going well modulo the current science funding landscape, in that Cosmic Explorer still does have some funding from the federal government to continue exploring the project. They're going through the process of site selection in conversation with the federal government, with state government, and with indigenous peoples, because ultimately, if you want to put a 40-kilometer long detector in the middle of ideally not particularly populated land, you inevitably end up crossing over some indigenous territories and traditionally and lands that traditionally belong to those people. And so the Cosmic Explorer collaboration has been working very closely with indigenous peoples across the Southwest in particular to find an appropriate site for the instrument. Tejas.
How's the digital from? Like what separates it from?
Yeah. So the real answer is a lot of complicated algebra. The short answer is that whereas in a Michelson interferometer, you have actual interference happening between your two laser feeds, in a digital interferometer, you're taking a measurement of the power and specifically the phase of each of your laser like data streams. And then if you take those two data streams and you combine them in a computer in very specific ways, you can essentially create that interference digitally by sliding the signals across each other with, again, a whole bunch of algebra to actually make it happen. But this allows you to do cool things like cancel out a laser phase noise that'll be present in LISA that's 10 orders of magnitude above the actual gravitational waves that we're looking for. Even beyond Cosmic Explorer and Einstein Telescope, which are pretty well-developed concepts at this point, there are further proposed concepts to fully expand the gravitational wave spectrum, not just in the hertz and kilohertz, where we have ground-based detectors, not just in pulsar timing arrays in the nanohertz, not just in future LISA in the millihertz, but across the entire spectrum the way that we have electromagnetic observatories today. In the decihertz, you have a number of proposals. You have the Laser Interferometer Lunar Antenna, which is being spearheaded by Karanjani, who's faculty here. You also have the Lunar Gravitational Wave Antenna. The former is a LISA-style triangle interferometer on the moon. The latter is using the moon itself as a massive Weber bar, a resonant detector. When gravitational waves pass through the moon itself, they will squeeze and shift it a little bit. If you put seismic sensors that are really precise on either side, you can start to be able to observe that. And what you're going to get in the decihertz, you're going to get white dwarf binary mergers and gravitational waves, which unlocks the possibility for multi-messenger supernovae, specifically type 1a supernovae. You're going to be able to measure with unparalleled precision the precursors to mergers in the LIGO band. So you can get incredibly good sky localization on them before they even merge, and you can have telescopes waiting, and you can make sure your gravitational wave detector is on when an interesting signal is going to merge. And there's a lot of discovery space in terms of potential dark matter signals around supermassive black hole binaries and things like this. Oops. You could also have a decihertz concept that is out there in a solar orbit in the way that LISA is. The basic idea there is just you have a set of smaller LISAs that are somewhat overlapping. If we go to lower frequencies in between pulsar timing arrays and LISA sensitivity, you have a band that is really, really rich with massive binary black hole physics, as well as a good number of both galactic and extragalactic stellar sources far from merger. And so there is currently a call from ESA, Voyage 2050, for their next set of large-scale missions. And one of the things that ESA is looking at is a LISA successor. What are we going to do after the 4 to 10 years of LISA observations in space? What do we want to do next? Several of the proposals for that are microhertz observatories that would essentially be solar system scale observatories, where LISA is 2.5 million kilometer arms. Again, to go to lower frequencies, you need to go bigger. So MUARES is a proposed concept that would span the Martian orbit. And LISA Max is a concept that would span the Earth's orbit, whereas LISA is more or less following the Earth. LISA Max would have a satellite kind of near the Earth, a satellite on the far end of Earth's orbit, and one more on the other far end of Earth's orbit to make, again, a kind of triangular configuration. There are also other concepts to be able to do microhertz detection. Blossom Jenkins pointed out that a pulsar system, if it's in a binary with a pulsar in it, and you are timing that pulsar really precisely, Paulson Taylor already showed that you can see the signatures of gravitational wave radiation within the pulsar system. But Blossom Jenkins pointed out that you can use the binary orbit as a resonant detector, just like the Weber bars, but on a much lower frequency scale. And Matt Miles here has actually been working on some of the concepts related to these sorts of pulsar binary resonance detectors, and you can ask him more about that. You can also do cool things within the solar system, like if you put some little transmitters on asteroids, or create an artificial timing array within the solar system itself, or send satellites that are sending laser ranging back and forth. You can start to do some sort of microhertz concept as well via the same technology that we use for GPS on the Earth. So that's it. This is a lot of words, but the main takeaway is we're in a really, really incredible era of gravitational wave detection. We're past the first detections, the field has opened up, and now we're starting to do the same thing that we did with light-based observation for the gravitational universe. Every single time that we have moved to a new part of the electromagnetic spectrum, we have discovered things that we never thought we were going to find there. That same thing so far has been happening in gravitational waves, and as we continue to fill out that spectrum, we're going to be able to discover things that we can't even imagine in this moment. Or we might just see exactly what we expect to and measure that incredibly precisely out to the very boundaries of the history of the universe itself. So I will leave this cute little thing up there. And if you have any questions, I'm happy to chat either now or later. Thank you.
People ask questions, if you find questions.
Yes.
I understand the appeal of the moon. We know truck driving, but why the moon? The doesn't.
So I've also been at times skeptical about the lunar concepts. It does seem expensive. I was at a session at AAS the other year in which one of the folks made the most compelling argument that I've ever heard. The science itself is all very cool, right? But specifically doing it on the moon, as you say, is going to be a large technical challenge. But the point that she made was that the Artemis missions are happening, whether or not we have a science case for them. So we might as well have a science case for them. A lot of that expense is already being made. We're putting things on the moon. It'd be cool if one of the things that we put on the moon was a gravitational wave detector.
Right, when you talk about the global, I am because this fight, and I think that you're gonna talk about that topic more we could. But just as a quick heads up, like, what are the main struggles and problems in such a big problem to the data, especially considering generally speaking different landscape of sources and how one can interact with the other. Is how can you do this up?
Yeah. The previous question was why the moon, and then I immediately forgot what Stephen said about repeating questions. This question was essentially, how do you do a global fit in practice? There are all sorts of problems that you might encounter when trying to sample that kind of large and dense parameter space. What is the route that we take to actually doing this kind of sampling? And you're right, it's a sampling nightmare, right? It's really, really, really hard. This is part of why we have an international effort that has been going for, I'd say properly about a decade or so, maybe a bit more than that, and will continue to push forward over the coming decade until launch to make it happen. The way that we do this in practice, and I can show you a little diagram, is via something called blocked Gibbs sampling. And so we take the idea that all of our different source types, a lot of them actually probably aren't correlated with each other. If you have a massive binary black hole merger, this thing is like SNR 1000. It's super high above the noise. It's doing a very specific kind of chirp that we expect to see from a binary black hole merger. And that's probably not going to be incredibly well correlated with a galactic binary that has a frequency higher than any of the frequencies that the massive binary black hole merger is transiting, right? So we can expect that certain source classes are not correlated and hope that we're correct in that, but we're pretty certain that this will be the case. And then you break out the sampler into like 10 different samplers in a trench code. So you have one analysis that's entirely focused on search and characterization of massive black hole binary mergers. You have one analysis that's entirely focused on the 10,000 or so observable millihertz binaries in the galaxy. You have one block that's focused on the combination of the instrumental noise, the confusion noise from all of the other 30 million galactic binaries, any underlying gravitational wave backgrounds or foregrounds from extragalactic sources, one that's focused on LIGO precursors, one that's focused on extreme mass ratio inspirals. And each of those is in itself a really difficult sampling problem.
Break that back to smaller bands, or
so we do that as well, actually. So the blocks are by source type, and the idea that we can parameterize and infer all of the aspects of a given source type at once, holding everything else fixed at whatever state it was last. And we'll talk a lot more about MCMC sampling later on in the summer school, so come back to me later also. But then you're right, we can also expect to be able to, in some cases, have a lack of correlation across frequency bands. And so for the galactic binaries, for example, when you're trying to solve a problem with 100,000 parameters, because you've got 10,000 individual systems with 10 parameters each, a lot of the systems are not actually connected to each other because one's at 3 millihertz and the other one is at 1/10 of a millihertz, right? And so you can try to break it apart into individual frequency bands and do the inference there. And then you have to do some complicated hopping back and forth to make sure everything talks to each other across boundaries. But that's absolutely one of the strategies that we use. But overall, the whole thing is really a practice in practical application of statistics and sampling techniques that is pushing the boundary of what we've tried to do in terms of scientific inference. Yeah.
All of
Hmm?
them. If you mentioned like you can solve the 100,000 parameter problem, like do you think that will happen? And what would be like, what would you happen? What's the strategy?
Yeah, so it's really not that binary in the end. You can be very dramatic and be like, what if the global fit fails? Realistically, what will happen if there's, especially if there's a common loud source type that we're not expecting, we'll have to figure out what it is and then start modeling for it intentionally, right? But probably what will happen is that if some part of our sampling process is starting to break down, we'll see the really loud things anyway. I mean, there are going to be SNR 6000 massive binary black hole mergers in there. You're not going to miss them no matter what you do, right? You might slightly mismodel them because actually our current waveforms aren't precise enough to be able to model an SNR 6000 binary black hole merger. But that's a different problem. You'll see it, you'll know it's there, you'll get reasonably correct inferences. And then as you go down in amplitude, you'll just start seeing a confusion slurry of everything else if you're mismodeling things. The concern really, because at this point we have prototype global fits that do a large part of this problem, not all of it, and on, although advanced, but simulated data. We don't have real data yet. So we're fairly confident that we are getting to a point where we'll have something that will run and give us answers when Lisa flies. The thing that keeps me up at night is that if we are not modeling things correctly in some or a couple different areas of the global fit, it's not that we'll immediately see, oh, the global fit failed. It's that we will get an answer and that we'll get a wrong answer, right? Exactly. And you will, right? If you're mismodeling power somewhere, it's gonna get put into the model somewhere else. So the way that we're trying to mitigate the impact of that is that there are a number of pipelines to do this that are being developed independently and in parallel. And the hope is that when the mission flies, we'll have pipelines across several different groups in Europe, as well as one out of NASA and potentially some community ones that we independently run. And ideally, they agree to some level. And that's what we've been seeing so far with the prototype ones, is that while they disagree, certainly once you get down to lower SNR and more confused sources, for your sources that would be very confident detections, for the most part, everybody finds them. So we get to do sort of a statistical and virtual cross-check in the way of the LiDAR detectors physically making sure that you see the signal in both detectors the way that you expect.
One more general question. This very fantastic overview. Just kind of curious, is there any specific thing that you're in particular really excited about, a result now, either in the Lisa era or in the next 10 years before Lisa changes all of our lives, that, you know, that should be the thing that's on our radar?
So the question was, what's the thing that I'm most excited about in terms of major discoveries across the gravitational wave spectrum, kind of in a little bit of a sneaky two-parter in the next 10 years and also in the Lisa era and beyond. I'll take a little bit more to think about. I think next 10 years, ideally we see an individual supermassive black hole binary and pulsar timing arrays, right? And that's me in part pandering to the crowd here. But I think it really is true that that will be an incredible discovery. It confirms that the background that we're seeing is in fact sourced from supermassive black hole binaries. It has a ton of multi-messenger applications that we'll talk about throughout the summer school. I think it's also going to be very, very interesting to see where the population of LVK detected mergers goes over the next 10 years. You know, from the plots that I was showing here, let's see, there we go. Again, that first little bit is everything we saw in our first two observing runs, and then we got tens of systems in our third observing run. And this doesn't even have the last chunk of O4, which hasn't been fully published yet, O4C, which, and we put out alerts for this, we have a lot of binary black hole merger candidates for that as well. And so the number of systems that we're observing is just exploding. And that's providing us with some unparalleled views onto what the overall population of these systems looks like. And that's already starting to both answer questions that we've been wondering about and create more questions that we get to spend the next 10, 20 years, possibly until we have Cosmic Explorer and Einstein Telescope to wonder about. Because a lot of these questions, I think fundamentally we're not going to be able to answer until we have something like every single system in the observable universe, and then you just do a lot of work and get all the answers. In the LISA era, I'm personally really excited about the amount of like stellar evolution science we're going to be able to do, as well as the amount of galactic science, right? So LISA is going to see every single close stellar binary in the Milky Way. And that's 10,000 of them as individual signals, and the rest is the sort of confusion noise that I spend a lot of time thinking about how to characterize. And we don't get to do that in the Milky Way, full stop, period. When we are looking for white dwarf binaries in the Milky Way, we have a complete sample out to maybe 100 parsecs. And then we have some scattered examples across some parts of the rest of the galaxy. But the galaxy has a lot of stuff in it, and specifically has a lot of dust in it. And so we don't know what these populations look like in the galactic center. We certainly don't know what these populations look like on the other side of the galaxy. And LISA doesn't care about any of that. It'll see right through the entire galaxy, and we will get a map of the compact stellar binaries in the galaxy across the entire thing. We're going to be able to map out the spatial distribution of those systems, constrain some questions about galactic morphology, and really study our galaxy in a way that we've never been able to before. And then also unlock the ability to study our own galaxy through a multi-messenger lens. The other one that I will say is, which is not my area of expertise, and I'm not going to spend a lot of time on, I'm just excited to see the results of everybody else's labor, which is precision tests of general relativity. Something that's really, really cool about, oh God, am I going the right way? Yes, yeah. Something that's really, really cool about these guys at the top, the extreme match ratio in spirals, is that when you have a supermassive black hole, and then you are studying the gravitational waves from a compact stellar mass object that is spiraling around into it, essentially what you're creating is a precision map of the space-time around a black hole in a way that we do not have the ability to do in literally any other setting. It's an incredibly difficult problem to actually solve. But once we can, and we're making really good progress towards being able to do the actual analysis, we get to measure and map out the actual space-time to a degree that has frankly been unprecedented in any other studies we've been able to do. So I think that's going to yield some really, really cool results about just black hole physics in general.
All right, Alexander started quite a bit. Let's. Great. All right, so we've got an hour now until the software help desk at 2 p.m. What I'm going to suggest is that if you haven't already put in your slide that kind of introduces yourself to the summer school, Lucas and Sebastian posted the link to the slide deck or to the sheet that links to the slide deck on Thursday. So scroll back in the main channel of the Slack and check there, drop in your slide, put in your interests or something about yourself, and we'll try to go through those later on. In fact, let me see if I can share here and we can get to that point.
Just to clarify, so all of us should do like a single introduction slide and then we can additionally volunteer for.
Yeah. So everyone should put in their own kind of introductory slide. Just tell us a little bit about yourself, where you're coming from. And then if you would also like to give a research talk or something about what you're working on, you can also do that in the mornings between 9 and 9:30 before we get started on the main lectures of the day. That's optional though. Give me 1 second. I'll try to bring this up. Okay, so scrolling back here, you'll see that Lucas posted this and Lucas and Sebastian are organizing these talks. As we just heard, there are 2 varieties, but please try to drop in a slide about yourself, within the next couple of hours so we can go through everyone who's attending the summer school, and that'll help us do a little bit of speed networking later on. And then since we've got an hour until the software help desk, you can go and grab some coffee. There are places that are about a 10-minute walk away from here that I think do decent coffee. I don't know decent coffee by Italian standards, but I think the Australians are snobbish about coffee as well. So Matt can suggest where you can go for coffee. I think there are 3 or 4 places within 10 minutes walk. Osa Coffee, The Well.
Our will says I know, shopping.
No, Osa is the only good coffee. Well, let me see if I can bring up a map that shows where these places roughly are. Okay, so you've got we are here. This is sometimes called the 17th important building or the Sony building. And then this is maybe about a 5-minute walk away from the top of those things. So that's 1 block down and then 1 block over. And then a bit further away, there's the Well, and then beside that across the road is Silver Fox. So the Well Coffee House and Silver Fox are, I think, 10 to 12 minutes walk away. So you've got an hour, and if someone was going to go to one of those, maybe they would lead an expedition. Matt, are you going to go to Osa for a coffee? Yeah, he needs more coffee. Okay, but let's try to reconvene at 2 p.m. back here. And we'll try to get everyone set up with the software they'll need, at least to get going. You might have to install more software as the week goes on, and then as we get into next week as well, but at least we'll give people a foundation. Matt and Nima are smiling at the back of the room because presumably they're trying to get something that people can install. We'll work that out. That's why we have the time for the software help desk. All right. And for the people online, we're going to take a break for the next hour and be back at 2 p.m. But 2 p.m. will be the software help desk. And that's just the next hour since we're on the different time zones. Okay, we're back. Thank you for clapping back to me, Ivan. We've got a while now to make sure that everyone's software is set up correctly. Matt, Nima, and Claude have worked on a way for you to easily get things set up. So I'll ask Matt and Nima maybe to come in front of the room, share those screens, and just talk through how you should install your software. And inevitably, we're all on different machines here. There's some Linux, Windows, and Mac machines. So there are going to be issues. There are going to be version problems. But that's why we have this hour and 15 minutes to work through it. So, guys.
Yes, or,
And if this is very easy for you, if you press one button and everything installs perfectly, then that's fine. You can work on your one slide introduction because we're going to do like speed networking later on. Okay.
okay. So what are we showing?
Just maybe start with the GitHub page, go through that. We can have like simultaneously go step by step. So ask people just first to get like create a repo and then move to the next step and answer questions as we need.
What is the next step? Go grade it, like pull this first.
So the first step is to get the code.
Yeah.
I think adding like a zip is easier. But download the zip.
Then yeah. Okay. Okay. Hello everyone. So I've just posted the link to this on the Slack channel. This is a repository with some of the materials, and it will be updated as the presenters finalize their materials throughout the week. But what we've done so far is we've gotten this Pi project TOML, and the idea is that this should be sort of like the secret key to install everything you need. So if you can go, if everyone can jump onto this link when you get into your Slack channel that I've posted there, and then just pull the GitHub repo. And does anyone not know how to pull a GitHub repo? We're all good? Yeah, cool, fantastic. So clone that or download it as a zip if that's a little bit easier for you. And then we're going to use a UV zip, which is a type of environment.
So if you've ever used Python, you know the dependencies can be a bit crazy. Conda used to be the standard for this, but it's bloated, and we don't want to just have your laptop having like 10 gigabytes of it filled with Conda stuff. So we're using UV. This is the first time we're using it, but we tested it. It works fine. So it's a lightweight package manager. That's all it is. If you've worked with virtual Python environments, it's the same idea here. It's just managed by this UV package. So the first step after cloning this GitHub repo is to install UV. And it's just one liner. I hope yes, it's what Matt is hovering over. Just one liner, it installs UV. And after this, we should be good to go.
Yeah, I am noticing that we don't have any Windows instructions here. Does anyone have a Windows computer that they're using rather than a Linux environment? Do you have a Linux environment on your Windows? Oh, that should be fine. That'll be all good. Is anyone determined to use PowerShell for some reason?
Don't be.
It's like Windows speaks a language that I mean, you know, I've never tried. One day.
Nope.
No, I
No
got
day.
no, we're not gonna do that. It should be. It's yeah, that should be absolutely fine. But just if you have any issues, let us know. But yeah, follow this, and then Nima and I can come around and give you a hand. But yeah, we'll have to probably repull this repository every morning. For instance, I haven't put my teaching materials there, and I'm teaching tomorrow. So yeah, we'll be sort of iterating on this as we go. But as long as the sort of the install works, it should be all good.
Ideally, if you're using Linux or if you're using Mac and you already have all the prerequisites, like the site is sparse, it's just one liner. If you scroll down now. So this UV sync active should be the only thing you run, and we'll install every package that you should need for this week at least. So it should go pretty well, but obviously we are here for a reason. If it doesn't, just let us know. Yes, Tejas.
So do I need to be all correct before I can move on to the next step, or is it just that I can it's just going to step 2 where
You gotta make sure you have all the prereqs there. It won't run without the prereqs.
so I need UV, I'm using active, so I need UV as well.
You need UV, you need scikit sparse, you need those two. Those are the prereqs.
I've never heard of UV before today. Have you used it before?
I've seen it used before, never wanted it because never had a reason.
Yeah, I mean, Mamba works really well.
Yeah.
So. I had you've used Pixie, the Pixie like things? Pixie files?
I don't know.
It's Scott Ransom.
If it was my own machine, I would just do a Python virtual environment, brute force install everything.
I can't stand virtual environments. If I'm going to use a virtual environment, I'll just use Mamba so I can basically get my computer malware. It's easy though. It'll never come off. It's gonna be fun.
Immediately software help desk channel, so if people have problems or issues or want to share advice that they've uncovered, then just put it into that channel. So.
Oh. Really visible.
Yeah, that's what I was trying to do and couldn't get VS Code to recognize it. I think my environment is completely cooked.
Interesting. There you
Equals or is it with different factor?
go. Sorry, say again.
Equals fit install or is it a different package?
I think the pip installs into UV. So yeah, anything that's like a pip installable thing should be able to go into whatever the UV container. Oh, okay, cool. Have you used UV before? Oh, cool. Do you rather it than Conda, or is it like, what's your thing? What's your favorite? Yeah?
Yeah. I previously owned these Hatch. I don't like them, but
Do you like Mamba? Is it like, Conda is the issue? Is it just slow, or is it like, yeah?
Too much unnecessary crap.
Yeah, people, like all the HPC people tell me that like Conda and Mamba is basically malware. But like,
No, it's not
I like
malware,
it.
it's
I
just
like it.
loaded.
Yeah, it's bloated. Yeah. Converge. Yeah. It'd be nice. Well, HPC should be built around Python at this point, I think, rather than C. I think that's my hot take. It really, I mean, you know,
I don't think engineers care about Python. And they
engineers,
get all the money, they have all the
but like,
status.
but engineers care about like fluid dynamics things. They have like whole other packages and stuff. I don't think they.
None of us is an engineers.
Yeah, I don't know what engineers do. I mean, I was an engineer, but I can't remember what I did.
You didn't use Python.
No, I used MATLAB.
There you go.
It wasn't good.
R and MATLAB.
All those planes I helped build. I didn't go anywhere near them.
Where's your loyalty?
I was not with Boeing anymore. So.
We're on Python. Yeah, because the GPU would give us a bit of nightmare. Because some people have Mac, some don't have an NVIDIA GPU, so like it would just cause.
But this has a GPU in it, right? It just isn't recognized by code. No
Who knows,
GPU.
who knows how it's
Yeah,
gonna
okay.
run?
Yeah. This is fun. You do like a straw poll. What's your favorite thing about gravitational waves?
Data analysis, like,
Yeah,
that's fun.
me too. Yeah,
It's like solving a puzzle,
yeah, that's a good thing. Yeah.
but you don't know the picture you're solving, you're just putting it together,
You,
but
you,
whatever.
never, you never know if it's
Yeah.
right. You have no idea if it's the picture you're meant to get. Yeah, it's good. It's gonna grab my coffee. What's your favorite thing about gravitational waves?
Like gravity.
Nima has answered the data analysis.
I think they're very clean, right?
Oh, that's a good point.
Because they're just with the electromagnetic waves, it's all very, there's matter, there's different radiation fields. You need to know the equation of states of things. Gravitational wave.
I guess of the gravitational wave sciences, PTAs are probably the dirtiest. You know, with the most.
Because it's more, the noise is phenomenological.
Yeah, like
We
the
don't really
ion.
have a physical. Yeah, I hope people on YouTube are enjoying this thing.
We've had some really good.
I think you've got them.
Hello.
You did that.
I'm sure. Yes.
So.
That's what I was asking. Final, but it's super.
You might have a problem. Right, and like, one, yeah. If I would have. First time, it's actually, you're not going to use it. And some people just.
It's not really.
Yes.
This is.
Yes, I did. Yes. This is.
Oh, I see. Cool. Just pretty cool. Yes. There.
No, is there any way that's smart? No, the sheets.
I know. We'll take camera.
Well, so I'm trying to call the main actions of the, nothing to
Yeah.
that, but it's just joking. Like, you said, reading something.
That's it. If you want to,
No, I'm not. I think it's something higher. Yeah, I got just see. Something. Should be.
We already on the clock there?
Yeah.
You should be able to change the fact library. You go to get it off of.
Yeah.
There are, you open
Yeah, no, I mean, I'm. Smart. Yeah.
I should be done, I was in the condition.
Is easier.
No, it does.
I'm calling. So.
What does it tell you? And just, but then tell like. Yeah. Sure.
Yeah.
Oh,
Yes. Yeah.
Yeah. Yeah. What flavor of lemon? Color. Yeah.
Sure I am.
You can do UV
Well, maybe,
Oh, this is my car.
This should be bigger than everybody knows.
Actually.
I'll keep you.
Well, yeah.
The way that. It was made like that. And maintain water. You're going to decide. Okay, probably have some. You can just show it. I'll come back to something is getting very long, they can deal with it. I think it's fine. Yeah. So you know, does anyone about Friday come here?
Yeah, this is something that I just, after I managed my school.
Were you connected to this website? Yes, it's true. I think it's just, if you run it again, if it's cash, they have one of the community card, you can try it. Yeah, just there's until just on time. Before you get it. Yeah, they do it more, so they're gonna look at it. You're not going to do such a. I'm just thinking,
like, yeah.
And you.
I can.
Around her Twitter.
Interesting.
Yeah, it is. Yeah.
Okay, so I'm sure it's still. So. No, you are not. Like, what we will.
You are. You are. It's signed the
As far as the many,
Does anyone have this scale open, on as space force? Okay. This deal. Oh, on the. It seems like it's the streets.
Yeah, that makes
I mean, we start with always difficult, but but it was more. We had to. Okay, so the factor that was doing that is going to be more popular. Oh, it is. You have to do. But sorry, you can. Yeah, well, that's not good. Yeah, we did it also. It might have to be, but I'm going to. I need a fun drawing because I'm not there because I have. But I didn't. You very good. You want to say? Okay. All right. Yeah. That's why so this being when. So we got the
Yes, I did that.
You know, we're going to Carlos with it. Yeah. You can run it out. Yeah. Yeah, I made that you be like the same. Okay. Maybe collective guess. It might be that some of the time, it's going gas, it's only certain part, but everyone might guess. Thank you, yes. Well, balance of motivation here, but if you want to get around to like mess up, we all might get ideas to the curriculum. You know, at any point, you can just create just something for out. Yeah. I really, yeah, I really just for about. I think, I've been graduated in all that's probably, I think branding, I think you're better off more people figure out about it, but, now, yeah, I think, yeah, it's go. They might be a gas, now I think they don't win. This is plan and the inversion, they just going to, he's going to guarantee that the ours, amongst themselves, look cool. Yes. You control people. I know what. It seems to be, let's see, let's go. Yeah. It happened when we moved, somehow. And I would want to. Somewhere. Thank you. I'm right. You should have
It's a hard. I'm just trying to freeze the version that I sent.
So, well, everything you're gonna do, you should be able to pump it up. And sometimes that you can find it. You're not gonna run it.
Well, it's not full enough. But
I mean, you're going to try to find that.
But I only first result that for that.
It was your.
So it means.
I just need where.
There's gotta be an option. It's smart, they're thinking about how you can. It's very important.
Yes.
Oh, maybe. Yeah, that's fine. That's the.
You should put it on board.
So we'll spend about 10 minutes just making sure things are installed. If you're encountering some roadblocks, don't worry if you don't get it installed within the next 10 minutes. There'll be plenty of opportunities for help desk, so we just wanted to use this to at least share a problem. After that, 3 o'clock, we'll take a coffee. Hydration break. Yeah, yes. Well, not hydration break. And then we'll do some sharing of slides. If you haven't got your personal slide yet, slide deck, and now a chance. And then we'll do a little bit of speed networking. One-on-one, asking each other questions, we're taking it around for 3 minutes. We'll see how that goes. It's quite more. Maybe a little bit, but that's
All of our. Yeah. Yes. Now, yeah, just work. So it's true. Oh. Yeah. No, it's okay. This one is wired. Sure, you can, if you go to the GitHub and do the setup at fine, you see a manifold. You may want to do that, but it lets you, it will tell you anything, because that will take you too long. You just gotta go through everything, why you can see it, and by the way, just every now, for now, you can just single, and then Jack is compatible with your machines. And then okay. Yeah, so the installation of everything is done, right, to the web. It's sort of cover the house from this. And this is long order. It goes there on half. These are. Sorry, Is that doesn't be? So these are the ovals. Yeah. Can you just try running this like once? No, I like run for nothing. Okay. That can make worse. No. We were arrogant.
Yeah, we got everything last week. Oh, yeah, last week we had like exactly this time.
Yeah, because you can have so
I
many.
think that was ours.
Yeah, right, there you go.
Yeah.
I see.
Yeah. Before. No, it's crazy when I did this. That would like.
Yeah.
A year ago.
Oh, there's something that I didn't look very familiar.
Yeah.
It's like when you said, I was like, well, it's still. It's only keep one of the games. Okay, so I was looking at, yeah, okay, so it's like, I think it actually had somehow used working out, so it seems to be. Yeah, I think this.
Every time I used it, it's a little bit weird.
Well, it's also a new thing, you really found very cool.
Is there a reason you're doing this? Yeah. I mean, I guess that way it's easier. Well, I was able to do this song.
Oh, rather than what we're going to do, bro. You probably want to do this. I think it's good. The other guys are doing this just, because it's just
Yeah, awesome.
That's good. How something's really.
Very good. I was able to that junior line of the that we continue working with everything I've done.
It's good, yeah. They bring it.
Yeah, there is that.
Like, they're just like very smooth. Where was I?
Sorry.
Yeah.
Yeah.
Okay, grab a snack if you need one. We'll start during the kind of speed networking in about 15 minutes, okay? And if you haven't finished your slide, now is a good chance to do that.
Well, here's a
People mostly got there with solution.
Yeah, there's just a few people who are, basically two people that are struggling. So should be cool.
Thanks, Matt.
No worries.
Nice to
Oh, okay. I don't know. Super cool. So
You just gotta play part of the. You could give this, so.
also, you're not going to the mile, get out of the field like that.
I think so, it depends on what you guys want to do. Yes, I think if you're already on something.
How was it?
I mean, sure.
That's a good idea. It works around.
Okay. I'm not really so from the. You guys.
That way.
I think it's all going.
Yeah.
No.
Well, that's no plan.
So I suppose that this is all.
No, I say it.
Well, yeah, I made it, I told you, right,
Yeah.
and so
I think so. It's how this is a habit for the recruit that means.
it's just this.
Yeah. That's.
Okay. Don't do anything, you want it, or. Oh.
My engineering, that is not my power, is
I think it's best to do that, so I want
Oh, you didn't? You did. I don't know. It becomes forever. Just, yeah. So apparently, you have something. I think you have fun. I thought, you know, right there. That was giving go. You're in, so strong. Yeah, that's, it's what I usually think for. You're in my. Here. I think this is. Okay, how do I now? Oh, I like that. No, you both also. Yeah, you can just simulate. No.
Oh, it's.
Instead of, I think it's really important, they all go through things that good apples or.
I know what you're doing. And it's really impressive. Both of them. What like to find fruit. Longer. Not now. That's so this is you can also this company you're information
Yeah.
I would run him again all the time. Okay. Yes.
That's it. I'm pretty sure I didn't need to and correct. And then. Actually, we're doing those are fall. Of course, I'm not in good idea. That's why I should. One of the operating. Depends on going. Or maximum today. The other thing is, maybe so you go to pull the so you don't better. Yeah. And then yeah, go wherever you want to now. Thank you for and then also see that and
Because my life, is about the marketing response, they're not academic. Yeah.
They give you. Yeah. I don't know. I want that whole thing. Yeah.
Actually, John. It wasn't. Not always. I see your hands in your how I say. Yeah. I didn't do it.
Now, yeah, but now we go, now we go to now, what happened is the family should have. Yeah. And then you are.
All right, well, you know, you. Stay strong. Yeah. Yeah. He's got 0.6. Oh, wait, no, that's not. Yeah. Yeah.
Okay. Ready to start? So let me tell you how this is going to work. First of all, let's just go through one slide for each person. Just give a brief introduction of yourself, but it doesn't need to be too detailed because after we go through all the slides, we're then going to work in we're going to do like a speed networking session, and everyone in the room will do this. So you'll just go and sit down next to someone, and then for 3 minutes you'll have a prompt. And the prompt will give you something to discuss. Doesn't need to be that, just get talking. Share who you are, what your affiliation is, and then why you want to be here. And then we'll just circulate around every 3 minutes and you'll meet someone new, okay? This is also a good way to find out what kind of mini projects you might be interested in doing, which is something that if you haven't signed up for already, you're not quite sure which one might be in your wheelhouse, then take a look at those mini projects and see what most is calling to you. If you're not quite sure, then talk to one of the organizers and we can help figure out what might be good for you to get involved with. It also doesn't need to be one of the list of mini projects. You could also just make up your own and see if other people are interested. There are some people working online as well. They'll probably work on their own mini project. It's most, feasible for them to do their own mini project as an online group. But the idea is just to work on something in the next 2 weeks that uses some of what you're learning over these next 2 weeks. So without further ado, first up, we've got Lucas Spears.
You're moving to the front, sit that back here.
That's a good question. Why don't you come up to the front because we can catch you on the microphone then.
All right, I'm up first, reluctantly. I'm Lucas Spears. I use he, him pronouns. I'm entering my 3rd year at Vanderbilt's physics PhD program. I'm into physics, not the astrophysics. We have different ones. I'm probably maybe one of the few or only physics program in here. I'm part of VIPER, new edition kind of as of last semester. I'll get into that with my pictures up here. But currently my projects are performing optimal research on the optimal statistic in PTA analyses. So I'm from Huntsville, Alabama too. It's kind of known for being spacey there. We got the Space and Rocket Center, Marshall Space Flight Center, everything like that. Space Camp is there. I never did Space Camp, but I put some things that I like over here too. I enjoy watching movies. I like sci-fi. Dr. Zaius is my guy. I like the old Planet of the Apes. I like old horror stuff too. And my dad's a comic book creator. That's his comic book. That's the first issue of Monsters. So I put that up there because I love comic books too. And so we do that together. And this is a picture of the Millennium Falcon. in Galaxy's Edge at Disney World. Me and Steve talked about it a couple weeks ago, so I thought I'd throw it up here and show everybody. It's cool. So I like a lot of nerdy stuff. And I used to do research in like chemistry and kind of bio. And as of like December this past year, I completely swapped and decided I hated that, I think. So
You saw the light.
so yeah, I saw the light. But I'm here now after my awakening and I'm enjoying this a lot more. So but now I've completely flipped script and I think I'm doing well. It's been a lot better for me, so I'm happier. I think that's about it. If you have any questions about Huntsville, ask me.
Yeah, thanks, Lucas. Is this anyone? Oh, that.
Yeah, I'm gonna leave there, so.
Yes.
Yeah, I'm Sebastian Banzak, he here are my pronouns. I'm also in the VIPER group here. But I also work with AGM people. I'll get into my research in a minute. But yeah, I just finished up my first year here at Vanderbilt. I'm originally from Milwaukee, from Wisconsin, so big fan of all the sports there, if you know about that. I did an argument at Northwestern University where I worked with Kate Witt, who's their advisor right there. She kind of sent me on this path of research, and led me to apply here to Vanderbilt to work with Steve Taylor and Jesse Bruno. Generally, I guess, yeah, focus on detecting supermassive black hole binaries. I look for electromagnetic signals, indirect electromagnetic signals, specifically that's like looking for periodic signals in AGN light curves. But I'm trying to move into multi-messenger stuff, looking at single source detections, things like that. But yeah, I've had a good time this first year, applied to a couple of proposals, so definitely kept myself busy. But outside of school, I really like traveling. I like sports a lot. I love listening to music. Some of those are the albums that I was listening to a lot a couple of months ago when I made this slide. But if anyone wants to talk about music, I'm more than happy to do that. Obviously, we're in Music City, that's a big thing here. But yeah, I love the fall, so I'm having an awesome time. But yeah, I love the city. But if anybody has any questions about music, research, whatever, I'm happy to talk about it.
Thanks, Sebastian. Next up is me. So I'm Steve. If I haven't had a chance to introduce myself to you yet, I'm a faculty member here. I'm originally from Northern Ireland, which is the part of Ireland that's still in the UK. Yes. So my wife up there is Erica. That's us a few weeks ago when she was able to join me at a conference in Vienna. So that was really nice. I am the butler to this very precocious cat here, Olive. She has me wrapped around her little paw, so I do her bidding. And I like hiking, I like reading, I obviously like astrophysics and data analysis and GR, but I like a good cocktail and baked goods as well. So that's me. Everyone else got a round of applause. Next up is Levi.
Okay, hello, my name is Levi Schultz, I use she her all pronouns. Let's see, I'm a 4th/5th year grad student in Steve's group here at Vanderbilt. Okay, I work on looking at anisotropy of the gravitational wave background in PTAs, and I'm starting to do a little bit of research work as well. Outside of research, I like finding whimsy day to day in hikes or riding bikes or I don't know, whatever else. I put together the social document that is in the social channel. So if you like that, great. If you don't, you don't have to tell me. No, but in all seriousness, if there's something you're looking for that you don't see in the document, feel free to ask me or ask any of the other locals and we'll find whatever you're looking for. Yeah, let me know if I can help you have a wonderful time in Nashville the next 2 weeks. That's it.
Thank you, Levi. Is there a dedicated like whimsy slant to the social activities? We do in Nashville, we do have one of only 41 IMAX 70mm screens. But good luck if you're able to get a seat, because I think they're all.
Sit behind for peak and the start 30 minutes after the.
That's right. That's right. Next up is Kyle.
Hi everyone, Kyle, very lucky to be here. Pronouns. I'm a fifth or sixth, coming into my 6th year with my PhD. I also work with Steve here. I mostly do kind of everything at this point, but I'm an expert in the PTA on statistics. So if you have any questions about that very specific thing, I could probably help you. Other than that, I do have a precious little kitten. He's wonderful. I do some astrophotography from time to time, and I do like playing some video games, things like Street Fighter, like 5% in the world or something like that at this point. So, yeah.
Thanks, Kyle. I like the way you just threw in there, like, oh, just top 5% in the world. And next up is Nima.
I didn't know if I had this copy and paste from 3 years ago, 2 years ago. But all of that is still true.
But now you have a mustache.
Yeah, I know. Well, I had it. I am a postdoc here for another month. I'm trying to remember what to say. That dog right there is not my dog, that's my brother's dog. But I like him. More than what I can say about a lot of people. And I play a lot of video games if I have not doing data analysis. God of War is my favorite franchise ever. I built a lot of PCs. This was before these were somewhat, reasonably priced. Now I can't afford that, but I already have a very good PC, so I don't care. It's gonna try to go very hard. I used to play a lot of soccer before I hurt my knee. That's what you see R9 right in the top corner. I got my PhD from Oregon State University. Yes, I was the first graduate student at OSU to do local timing there. I led a nanograph project for alternative polarization, most of gravity, some of the stuff that you saw today. I got a lot of flashbacks to a few years ago working on that. And after my PhD, Steve hired me to be a postdoc here. And I do every type of data analysis imaginable gravitational wave domain. From making software, thinking about learning other people's methods and poking fun at them for making mistakes or simplifying things. That's my domain, so data analysis.
We're not clapping the poking of fun or point out mistakes. All right, next up is Matt.
Hello. My name is Matt, that's my face. It's bigger on the screen here than I thought it was going to be. I'm a postdoc, so I'm one of Steve's employees. I do a little bit of everything in PTA role, so I like lots of timing, but I also like data analysis and poke from holes and paper data analysis. It brings me great joy. I'm in a bunch of PTAs, but I would say I'm probably somebody who feels a bit more comfortable outside than inside. I love hiking and just being out amongst the world, going to see music and that kind of stuff. I'm terrible at guitar, but I have better opinions on music than Sebastian does. So if you want to talk to somebody, talk to me, not Sebastian. I am from Australia, but I'm a good part of it. Apparently, I'm fostering a dog, which I've called the Hound. This is this guy just here. I've only had him like 7 days,
But I was working from home last week and he's just staring at my laptop while I'm doing like work the entire time. He's incredible. He's a great astrophysicist. He'll be on this next week. That's good. But his name's Hugo. He's also got adoptions. If you're paying to stay here, $250, that dog could be yours. Great.
This is not a sales pitch, this is introduction.
That's a sales pitch. Yeah, you gotta sell yourself, Steve. So, I would love to keep that dog, but unfortunately I can't keep it actually today. I fall in love with this town. But someone please take it off my name. Anyway, that's basically it. That's, you can see there's a picture of Norway in your glacier down there. I really like hiking, as I mentioned. So if you've got any better hiking photos than that, let me know. I'm trying to be a crab here. You can't actually see it. But so this is me just here. I'm doing like a crab thing, but unfortunately it didn't come out very well. Anyway, nice to meet you all. Hope we get to know you better over the next week.
Matt is also an alumnus of the first summer school that we did here in 2022. Thankful.
It's not easy to slide, we have to come up to the front.
I didn't, it's just so it's recorded, really. If people do want to come up, they don't have to.
It's all good. Hey, everyone. My name is Thankful Property. I am a brand new assistant professor here at Vanderbilt as of July 1st. Really excited to be here. And so I'm kind of in the middle of my move from the DC area. I was doing my second postdoc at the Naval Research Lab. You can see some nice DC cherry blossom pics up there on the top right. All I said about my research is that I'm a pulsar enthusiast, which isn't wrong, but it's also not very specific. So I've been a member of NanoGrav for more than a decade now. I'm chair of our pulsar timing working group. And I also participate in the IPTA. I really like pulsars for a whole lot of reasons that I'll talk about tomorrow. But I like measuring their masses very precisely to try to constrain the neutron star interior equation of state, as well as getting PTA stuff. When I'm not working, I like whitewater boating and hiking, being outside, lots of art. I love video games as well. I'm currently obsessed, even though it came out almost a year ago now, with the second Death Stranding game. So if anyone wants to talk to me about Death Stranding, I'm here. But there are like 3 people, I think, who like that game. So, and I love, music and going to music festivals and all kinds of things. And this is my dog, Ez, in those 2 pictures, and he's a total goober. Thanks.
Was that in the sphere, Thankful? Were BTS in the sphere?
It wasn't in the sphere.
Oh, okay.
Yes.
Yes. Alessandro?
Okay, so I'm Alessandra also. I'm from Italy, but not from the sunny part, but from the cold, foggy, and polluted city of Turin. And now I moved to Germany. I'm at my first year of PhD at the University of Münster under the supervision of Professor Schmitz. There is a picture of where everything started and I graduated for the first time. And now I'm working on Bayesian inference, and I will work on model comparison for cosmological sources of gravitational waves using PTA data. I've been for some years in the dark side because I work for as an IT consultant in industry, but then now I return to physics. Besides physics, I enjoy art and music, especially drawing and painting. There is a picture of me with my Italian band.
Oh, cool. Very nice. So are you in a band? You're in a band?
Yeah.
Oh, very cool. That's amazing. Next up is Samuel.
Hello, everyone. That's me. I'm a PhD student in Milan, and I've been working in Alberto Susano's group on PTA astrophysics mainly. I like to do a lot of stuff. So as you can see, I tend to plan not so safe trips to places that are sometimes illegal to go to, but it's fun. And so that's me on top of a radar tower that you should definitely not go to, like 30 meters high, whatever. And then I do a lot of sports activities. I was in a football team when I was a kid, then I got drafted out because I was bad, so I stopped doing that. But I still root for my team, Juventus. And I play guitar. There's a few albums, so whoever is into music, we need to schedule a talk. And yeah, that's about that's my dog called Paquito, and he's in a very triangular shape right there. It's amazing. So that's my favorite photo of him. And then physics side, I work on SANS mainly, SANS and which is semi-analytical models for black hole populations and also hydrodynamic simulation. So I'm doing astrophysics mainly, and yeah, accretion physics also, because I used to do that for my master's before I enrolled into this PhD in the PTA group. So I'm new to the supermassive black hole stuff, but for now it's been great. I met a lot of interesting people, so I hope meet a lot more as well.
Yeah, thank you very much. I don't know if the buildings we have in Nashville are tall enough to interest you for your explorations. Next up is Darwin.
Hello, I'm Don Carlton. So I'm entering my second year PhD at Wake Forest University. I'm kicking with. I probably should have put more about research, but they're in like 10 minutes. So I'm basically just copying Sebastian. EM circuits of supermassive black hole binaries. And this was kind of the first year in this subject of research for my undergrad at Boise State University. And got a physics with an astrophysics emphasis. And I did a lot of observational astronomy was my main research. So like you can see that was the telescope we worked with, and it was named the Barney scope because it was pink, the realm's like hot pink, so it's called Barney scope. It's awesome. So yeah, I'm from Boise. That's a picture of Boise with the northern lights over it. And then most importantly, I'm a fiance of Grace, seeing the bottom left. And then I have my cats, Ocean and Gizmo. You can see Hoshi, he's the dark one that looks like he's not enjoying his life, but he loves it there, I swear. They just go into that window and then lay in the curtain and they like it for some reason. I don't know. Yeah, I'm also really into like music. Boise had like a local music scene, which I went to a lot of shows. A lot of like hardcore screamo shows and then like electronic shows. So like my main thing, I guess, I produce electronic music. The bottom right is me performing at one of the local shows in Boise. So I don't like play the guitar or anything, but I like play the computer basically. So I do it all on the computer. I kind of like fashion, but it's really expensive to get into fashion. So I mainly just thrift. I like old tech, like camcorders and cameras. And then like retro game collecting. So I don't know, maybe some people don't think the PS2 is retro. I don't really know, but
that hurts me a little bit. But yes.
Yeah, and then I also play video games. Like I guess I play a lot of Counter-Strike. Yeah.
Thanks, Del. Next up is Niana.
All right, I'm Niana. That there on the top right is her project, at least the most accurate one you'll find. Meaning I am at any point in time as happy as I am visible. I am. I'm happy but less miserable. I am at Penn State. I'm entering my 5th year this upcoming year. I primarily do quasar spectroscopy. I do a lot of radial velocities. I might have updated that slide to say that I'm now doing accretion disk modeling. And because I don't seem to have enough on my plate, I'm now trying to learn this field of PTA gravitational waves. I will complain about
everything that I do throughout my 2 weeks here, so you have not seen the last of me. Hobbies. I do not have many hobbies. I've been dead for about a decade. But as far as accomplishments over the past 10 years ago, I have completed 2 embroidery projects as shown up there. And these are all through class. I have decent friends who force me to take classes because they think I do not have hobbies, as I said. Anyway, yes, this is all you need to know about me. Here.
And a former Vanderbilt and Fisk bridge student, which is important to point out as well.
Yes.
Round of applause for that. All right, Kat?
So hello, I'm Kat. If you can't tell from the left side, I have one of my students. I did my undergrad at the University of Texas at Dallas and did it in math, so that's me doing my best to be a Greek mascot. Bottom left, I was on the National Council for the Society of Physics students in my undergrad, and of course, figured you guys might appreciate me meeting Jocelyn Burnell, while dressed as Professor Farnsworth. She had no idea who I was. She was very polite about it, but I think she was scared. All right, then after undergrad, I worked as a software engineer at the EMIT Observatory for about 3 years. So the GBT in the background there takes a lot of nanographs pulsar timing data, which is how I learned about pulsar timing. And also I'm currently working on a movie that takes place in Green Bank. We're in post-production now. So that photo down there is me and the director and the writer. 4 in the morning, about 10 minutes after we wrapped. It was exhausting, so keep an eye out for Green Bank in about a year, because editing apparently takes forever. And then now I am a graduate student at Oregon State University in Jeff Hasman's group, who is the guy with his arms up there. He's wonderful. And I'm also on the Department of Energy Computational Science Graduate Fellowship, which apparently means I know. I'm not sure I heard that, but that's me.
Great. So you said Jocelyn Bell Burnell was just like polite, but clearly didn't know what was going on.
She was like.
It's a very Irish way of breezing past the situation. Next up, Surajit.
Hi, so I'm Surajit. I'm a second year PhD student at Wake Forest University, starting the second year. I'm working with Gateway on the right corner. This is our only one picture I have in the gallery, and that's also special because that's first day for both of us. We started together in the job, and I did my integrated BSMS from India, Indian Association for the Cultivation of Science. I calculated quasi-normal modes for exotic compact object, but then Kathleen pulled me from the ring down to the spiral. So right now I am the part of the detection group. I am doing the supermassive, the continuous gravitational-wave detection part, and also working on some modeling project, which we updated in the detection group. And yeah, I'm just learning the process till now, mainly working with enterprise and trying to figure out cool GPUs, how to use it, and Prometheus. And there's like, I am not good at anything, but I have lots of hobbies. So I love to hike, travel, watch movies, photography, especially astro and architectures. I love to draw, read thrillers, hang out with friends. As you can see here, this is the first day probably. This is the first day we meet all the friends here in US, like after I moved into the Wake Forest. That's not a very good picture of Wake Forest, people also, but I bought a new mirrorless camera last month. So that's my first clicked image. And that's when I go camping, just put on my, I just lay down there and watch the sunrise. I like it. And that's me hiking. That's my girlfriend, Iman. She's at India, but she will probably move in sometime to the US. And that's my cat, Kit Kat. She also lives with her right now. Yeah. So that's all about me, and I love outdoor games much more than computer games as you guys. And I love cricket. Probably most of you don't know how to play that. And football. That's also like I thought it's not that familiar in US, but after World Cup, I see people watch soccer.
Oh, yeah.
Yep. That's all.
Great. Next up is Will.
My name's Will. I'm a first year graduate student at Georgia State University. Currently located in Columbus. I say currently because I've lived nearly everywhere you can imagine. My interest began in undergrad with supernova surveys, doing research with that. And then I went to grad school as a mathematics student where I took general relativity and decided that was pretty cool. And eventually I found that pulsar timing arrays are the best blend of the two. So observational astronomy and general relativity, and that's where I'm at today. I sometimes post astrophotography photos to my Instagram. It's pretty much my only hobby, but I've been able to do it in a long time because I've been building commercial jet engines. So if you guys fly Delta, hopefully it stays in there. If it doesn't, it's not my fault. That's my two kids. We were watching the Artemis, take off. The one I'm holding, his name is Tyrion. If we have any Game of Thrones fans. Wow. And the one that's holding the camera, his name is Tate, if we have any American Horror Story fans. And then that's one of my cats, and the other one is my pocket that you can't really tell there. Okay, cool. Me, guys.
Next up is Nathan.
Hey all, I'm Nathan. I put this together in like 10 minutes, so there's no pictures. I also flew in this morning, so I've been up since 2 a.m.
Oh, no.
So I'm kind of fine. But I recently finished my master's in health. I'm transitioning to a PhD at Oregon State in the fall, so Oregon State will give you a notes. I might have spent the majority of the last month, like all of my waking hours watching the World Cup. So yeah, huge like fan. Other interests, board games, Game of Thrones. But I've now cut up on House of Dragons, so please don't spoil it. And also One Piece. And yeah, that's.
Amazing for being up at 2 a.m. this morning and still being functional. Next up is Martini.
Oh, please refresh. I got it.
Refresh.
Thank you. Hi everyone, I'm Martine, age here pronouns. I'm coming over from Oregon State University. I just wrapped up my second year there and I'm beginning to project on hierarchical modeling and pulsars, but we'll get into that later. I have a ton of comments. I have a big life outside of physics. So I can be seen ramparting around with my partner of 3 years up in the left corner, Sonia. Everyone told me she's pretty, but not too much. Down below that, we have two lovely huskies. Apollo, which is our Malibu mix for side weapons. He's on the coffee table, and my partner's 5'7". He's huge and a huge cuddle bug. And then up there we have Sky, and she is the best rolling bowling in existence. After this picture, she did get those belly rubs stressed. I have to be seen playing bass, making dumplings, or many other things. Dumplings are a new reason to have a fascination. I now just have stress baking. I do stress make dumplings. Or sorting my collection of socks by genre. Feel free to ask me what socks I'm wearing any single day. I only wear novelty socks, and they're sorted by genre again in my hotel room presently. I am a huge D&D nerd. I don't have a group right now because of PhD reasons, but I really very much miss my group of 5 years from Georgia where I did my undergrad. So these are pictures of me torturing them. And then as part of that D&D hobby, I really love terrain crafting and mini painting. I did make that, we called it the Sentinel Wolf, and that was one of the big fights that they did. The Locked Tomb book series changed me on a molecular level. If you've read these series, please come talk to me about it. And also, I have questions for you. I also can be seen at shows of women screaming. This is my subgenre of music. Anything with women screaming, I'm there. So these are some of the shows I've seen. I'd love to compare concert rap sheets if you are also a big fan of women screaming.
What socks are you wearing?
For today, I'm wearing champagne socks. I thought it was good to settle.
Yeah, amazing, thank you. So we have something to add to the social calendar. We need to find out shows of streaming.
There's a lot of experience.
Let's go.
Next up is Tejas.
Good afternoon, everyone. My name is Tejas Mahesh, and I'm an undergrad at Vanderbilt University. I'm a rising senior. I'm majoring in physics and math. And I'm working in Dr. Taylor's research group for the summer and for the past 2 years, I would say as well. Right now, I'm working with Sebastian and Luna as well. We're trying to model accretion densities around black holes and seeing if we can understand and extract out features that can differentiate between AGNs and supermassive black hole binaries. Outside of doing research and school, I sometimes play violin. I was part of the club orchestra at Vanderbilt for the first 2 years here. One of the pieces that we played, and one of my favorite composers is Gustav Mahler. We played his Fifth Symphony First Movement. It's absolutely wonderful. I'm also a chess player. I used to play chess competitively when I was younger. Now, not so much. And there's only one really good chess platform, that's League Chess. Please not. I don't know. It's too gamified. Like, it's just minimalistic, simple. You know,
You want the purity of the game itself.
Exactly.
Let's go. Anyway, continue.
Other than that, I also like reading classics. That's kind of the current literature I'm into right now. I know a lot of people here probably like Lord of the Rings. I really enjoy the trilogy as well. But one of my favorite books is up there. It's Brothers Karamazov by Dostoevsky. Fantastic book, very philosophically dense, but I absolutely love it. Yeah, that's why I have.
Wonderful. We're all a very musical bunch, so we might have enough people to actually form a band. Dawson? Hi, I'm Dawson Gaynor. I'm going to be an incoming PhD student at Texas Tech this year. I don't have any of it up there, but I've done some work with PTA gravitational-wave sky maps before, and will probably continue doing that at Tech. I was an undergrad at Carthage College in Kenosha, Wisconsin. I'm assuming nobody's heard of it. It's a really, really tiny school. I'm a huge baseball fan. I played baseball there. I'm a really big fan of the Milwaukee Brewers. My dad's from Milwaukee. You'll see I went to several of the playoff games this last year, including all of the ones in LA that we lost all of. That's my dog up there. We got her before I went to school, and then I came back from college, and she now runs the household. She's about 20 pounds, but controls my parents. That in the middle is just a picture I took in the planetarium at Carthage. I was the president of the planetarium there, so I did a lot of shows in that. Yeah, I guess that's everything, but yeah.
Do you know that the Nashville Minor League Baseball team is theater for the Brewers?
Yes, the Nashville Sound.
There are games next week.
If anyone wants to go with me, message me.
They are super cheap tickets. You can buy tickets for the grassy area that's in the outfield and then just sit in seats. And then no one picks you up because there's always a.
Awesome. There you go. Kristen.
My coffee with me. Getting a little fussy, so he's gonna come up with me. Hi, I'm Kristen. Was Schumacher, recently changed to Allo. I am currently a joint NSF Ascend postdoc between Caltech and UT Austin. Just started this past year, so still learning. My scientific interests include a lot of tests of GR, especially modified theories that could have additional polarization. So Nima, I feel you. We'll talk more about that next week, probably. I've also worked a little bit on the cosmology side, like using gravitational waves to measure H0. And I make scientific visualizations in VR. So if you want to talk about that, let me know. I have a GitHub with code that anyone is welcome to look at, play with, do whatever you want with it, please. The more simulations, the merrier. Yeah. Outside interests, I have been in some version of choir for almost 2 decades now. And if you want to hear opera or like musical theater, let me know. I was in an a cappella group in college that did only musical theater, and that probably tells you everything you need to know about me. Yeah, right now hobbies pretty much consist of my family, and I do have a cute dog, so he's included. But yeah, this one is the biggest time commitment right now. This is GD. He's here with me for the next 2 weeks because he's not yet 6 months and cannot be without me, so.
Well, you gotta start him young.
Yes, we're starting him young. He's already been in several physics lectures. Beware, he does speak up, so, you know. He's always happy to add his opinion.
Thanks, Kristen. Olivia.
Hello, party people. I'm Olivia, Bitcoin, no affiliation with Bitcoin, unfortunately, for my financial situation. So originally, I'm from Chicago. If you have ever been stuck at O'Hare Airport or had a like horrible connection, I was right there with you, basically. I grew up like 5 minutes away. I've been a clown since day one. I'm a very unserious person. I feel like sometimes I come off as like, but just, there's not a serious thought in my head. I did my bachelor's at the University of Central Florida, UCF in Orlando. So that was a bit like a tropical vacation for me. And now I've returned to Illinois after a year of Fulbright research in Germany. So I unfortunately have lived in super flat places. I went from the flatlands of Illinois to even flatter Florida, and then where I was in Germany was also like the super flat part. So unfortunate for my hiking hobby. I don't think you can really even call it hiking. It's more of walking at this point, but you know, I'll take what we can get. Yeah, I currently do my PhD at the University of Illinois Urbana-Champaign, UIUC. And that's kind of in the middle of nowhere, like 2.5 hours south of Chicago, 2.5 hours north of St. Louis. But you should come visit us. We're super fun. We're super cool. I swear. They don't know that I do physics in a cornfield. I think that's a pretty accurate representation from we have a Veep account and stole that off of there. I just thought this was funny. I was actually here at Vanderbilt like 9 years ago, almost to like the week, just visiting as a prospective undergrad. So that's kind of crazy. My mind is a little bit blown by that. And these are some of my friends in my PhD program. I swear we're super cool. You should visit us. And the little creatures you see here are all of my godchildren. Yeah, my parents' dog, Kona, she's like half Great Dane, half Weimaraner, so very big, very sleepy girl. And then all of my friends' cats that I watch when they're out of town. So yeah, that's me.
Very nice. Are you a fan of ABBA or the movie Mamma Mia? What's the?
Like every year, our business department has like a gala type thing at the end of the year, and the theme was commentators. So AB minus BA spells out ABBA. And I was on like the decorating and the planning committee for it too. So we all had to be there to like show off our hard work. The title 36 10-inch disco balls by hand. And it was like, I kind of felt like I was in prison. So I documented it just to really seal the deal, celebrate the fact that it was over.
That's impressive. That's amazing. Wow. I think that's it. We'll give yourselves a round of applause. All right. Now we're going to do the following thing until we get bored. We are going to do a little bit of speed networking. So that means if you're not currently sitting beside someone, then go and sit beside someone. Don't worry, you're going to move somewhere else in 3 minutes. And we'll continue doing that, like I said, until we get bored. All right. Ready? You're going to receive some prompts. Okay, here we go. 3 minutes and then move to the next table.
I'm just gonna sprint downstairs and finish my thing for tomorrow. Yeah. What are we doing tonight? Is there a thing? Probably. Yeah, if you
Get ready to move. Move to a different table.
Okay, well, yeah. I'm still gonna call it that. Because the problem, I guess, with those is that they're different.
Hello, hello. I'm making a very brief announcement. You can go back to your network in a second, but I have city guides that have food and drink and fun things to do that are basically printed editions of one of the guides that I was working from, as well as this week's edition of the Nashville Scene. This has a ton of events listed in it for the next week, and also every concert venue lists their concerts in here and advertises them. So if you're looking for things to do this week, take a look through these things. They will have fun things. Okay, go back to networking.
Last question. Just. Some people want to go check. Okay, everyone, that's it. Give yourselves a round of applause for the first day. Okay, so, the evening is yours, but if some people were interested in going for a quick bite to eat or a drink, then there's a place close by called Jack Brown's. It's about a 10-minute walk away. It is, it's up to you whether you want to walk again in this weather. It's pretty much nearby the place where some of us got coffee this afternoon. It's up to you though. Go and do your own thing. Go and explore what Levi has to offer for national socializing. Otherwise, I'll probably leave here in about 10 minutes or maybe less than that, 5 minutes. If someone wanted to go for a bite.
Woo!
Yeah.